On a clear night, far enough from the city lights, you can see approximately 5,000 stars with the naked eye. It feels like a lot. It feels like everything. It is almost nothing. The Milky Way alone contains somewhere between 100 and 400 billion stars. Beyond our galaxy, there are estimated to be 2 trillion more galaxies, each containing billions of stars of their own. The universe is so large that the numbers used to describe it stopped feeling like numbers long ago and became something closer to poetry. Vast, beautiful, and impossible to fully hold in a human mind. And it is silent. Not quiet, silent. In 70 years of systematically scanning the sky with increasingly powerful instruments, in decades of listening, transmitting, and waiting, we have found nothing. No confirmed signal, no verified contact, no evidence anywhere in the observable universe of another mind looking back. This is the Fermi paradox, named for the physicist Enrico Fermi, who, legend has it, paused over lunch one afternoon and asked the question so simply it has never stopped echoing. Given how large and old and seemingly hospitable the universe is, where is everybody? It is a question that sounds almost casual until you sit with it long enough to feel its full weight, because the silence is not nothing. The silence is data, and what it might be telling us about life, about intelligence, about the fate of civilizations, about our own future, is either the most hopeful or the most terrifying thing the universe has ever communicated. Over 25 chapters, we are going to explore every serious answer that has ever been proposed. Some will comfort you, some will not. Some will reframe the night sky in a way that means you will never look at it quite the same way again. None of them will give you certainty. The paradox has not been solved. It may not be solvable with what we currently know. But somewhere in the silence, if you listen carefully enough, there is something worth hearing. Chapter 1. The question asked over lunch. There is a cafeteria at Los Alamos National Laboratory, and in the summer of 1950, a group of physicists are eating lunch. The conversation is light, which is not surprising given the people in it. These are men who have spent years working on things that cannot be discussed, in a desert facility whose existence was itself a secret, and the lightness of lunch conversation is earned and valued. They are talking about a recent newspaper cartoon that had been circulating, a cartoon poking fun at the strange reports of flying saucers that were filling the popular press in that period. The conversation is amused and casual and not especially profound. They are physicists relaxing over food. And then Enrico Fermi, who is arguably the greatest experimental physicist of the 20th century, who has won the Nobel Prize, who built the first nuclear reactor in a squash court under the University of Chicago, who has a reputation among his colleagues for asking the questions that cut to the heart of anything in a single precise formulation, says something. The exact words are disputed by the people who were there. The spirit of them is not. He says something like, "Where are they?" or "Where is everybody?" or some brief, light, almost offhand formulation of what appears, in the moment it is uttered, to be an obvious question about the flying saucers. But the question, even in its lightest form, contains something that does not evaporate when the meal ends and the physicists return to their work. The something is the beginning of a calculation, and the calculation is simple, and its conclusion is troubling. The universe is very old. Stars have been forming and burning for billions of years, and around many of those stars, planets have been forming, and some fraction of those planets have conditions that permit chemistry, and some fraction of those have the kind of chemistry that produces complexity, and some fraction of those produce something that can call itself alive, and some fraction of those produce something that can build a radio telescope or a spacecraft or whatever it is that would make them visible to us. Multiply small fractions by the enormous number of stars in the galaxy, and the result is still very large. And the galaxy is old enough that even a civilization that is only a little more advanced than ours could, if it wanted to, have spread across the entire galaxy by now. Spread its signals, if not its physical presence. Left some mark of its existence that we could detect, and we have detected nothing. This is what Fermi's question really is. Not a question about flying saucers, which he did not believe in. A question about the arithmetic. The arithmetic says there should be evidence of other civilizations out there. The evidence is not there. The simplicity of the question is deceptive, in the way that all the genuinely difficult questions are deceptive. The question looks like it should have an obvious answer. Look again at the night sky. Listen with bigger radio telescopes. Wait a little longer. The answer will come. But the answer has not come, and the waiting has been extended across 7 decades of increasingly sophisticated searching, and the silence is not getting louder. Fermi himself did not pursue the question. He died of cancer in 1954, only 4 years after the lunch, without having written anything substantial about the problem his casual remark identified. The question was reported by the people who had been at lunch, passed around in the way that good questions get passed around among people who think for a living, and eventually found its way to the researchers who would formalize it. The physicist Michael Hart published a paper in 1975 that is usually credited with establishing the problem as a serious scientific question. The astronomer Frank Drake had already been thinking about related questions and had formulated what became known as the Drake equation, an attempt to structure the arithmetic that Fermi had sketched in a cafeteria. By the time the search for extraterrestrial intelligence had become an organized scientific enterprise, Fermi's name was attached to the paradox that his lunchtime question had identified. A paradox is, strictly speaking, a situation in which apparently valid reasoning leads to a contradiction. The Fermi paradox is a paradox in this sense. On one side, the reasoning from the age of the universe, the number of stars, the prevalence of planets, and the apparent ease of developing technology suggests that intelligent life should be common and detectable. On the other side, the observation that we have detected nothing. The contradiction between these two positions, both of which seem to follow from reasonable premises, is what makes the problem a paradox rather than just a puzzle. The puzzle would be solved by more data. The paradox is solved, if it is solvable, only by finding which premise is wrong. The premises have been examined from every angle across the 7 decades since Fermi's lunch. The age of the universe is not wrong. The number of stars is not wrong. The prevalence of planets is not in serious doubt. The chemistry of life appears to be the kind of chemistry that the universe produces readily. The contradiction remains, the silence remains, and the question that began between bites of food, asked lightly by a man who was thinking out loud, more than making a formal argument, has become the most haunting unanswered question in the scientific landscape. Not haunting in the way that unsolved technical problems are haunting, because those have a specific shape and a clear direction toward solution. Haunting in a different way. In the way that questions are haunting when the answer might be something you would rather not know, when the silence that seems empty might not be empty at all, but might be saying something, and what it might be saying might be something about us, about what happens to civilizations like ours, about what is ahead as well as what is absent. The men went back to their work. The question lingered. Chapter 2. The numbers that should guarantee company. There is a way of doing the arithmetic that makes the silence feel like a mistake. Like someone must have made an error in the calculation, or the instruments must not be sensitive enough, or the search has not gone on long enough. Because the numbers, when you actually sit with them, produce a result that the absence of evidence seems to simply contradict. The numbers say there should be someone. The sky says there is no one. One of these must be wrong, and the numbers feel harder to argue with than the sky, because the sky is what we see, and what we see is limited. And the numbers describe a universe that is vastly larger than any instrument we have ever built. Begin with the stars. The Milky Way, the galaxy we inhabit, contains somewhere between 200 and 400 billion stars. The uncertainty in this estimate is itself a number so large that most human intuitions cannot hold it as a quantity. The uncertainty range between 200 and 400 billion is itself 200 billion stars. The number is so large that any attempt to make it concrete through analogy collapses under the weight of the analogy. If every star in the Milky Way were a grain of sand, the grains of sand would fill several beaches. The number is not a number in the ordinary sense. It is a description of a scale that our minds were not built to inhabit. And the Milky Way is one galaxy. The observable universe contains somewhere between 1 and 2 trillion galaxies. Each of them contains its own collection of stars, ranging from dwarf galaxies with tens of millions of stars to giant elliptical galaxies with hundreds of trillions. The total number of stars in the observable universe is estimated at around 2 times 10 to the 23rd power, which is roughly the same as the number of grains of sand on all the beaches of Earth, multiplied by the number of grains of sand on all the beaches of Earth again. The number exists, but it does not mean anything to a mind that evolved to count the members of a small social group and estimate the distance to the next water source. The question is not how many stars there are. The question is how many of those stars have planets, and how many of those planets have conditions suitable for life, and how many of those have developed life, and how many of those have developed intelligence, and how many of those have developed technology, and how long those civilizations last. Identifying the variables that the answer depends on and creating a framework for thinking about them even before the individual values could be estimated. The revolution in planetary science that began in the 1990s and accelerated dramatically in the 2010s has answered one of Drake's variables with a confidence that would have surprised him. The fraction of stars that have planets is not a small number. Based on the data from the Kepler Space Telescope and its successors, the best current estimate is that virtually every star in the galaxy has planets, and that the galaxy contains roughly 100 billion planets in the habitable zones of their stars, the range of orbital distances where liquid water can exist on the surface. 100 billion potentially habitable planets in the Milky Way alone. The number is staggering, and it is, as far as the current science can determine, approximately correct. The fraction of those planets where life arises is the variable where the uncertainty explodes. We have one data point: Earth. On Earth, life arose relatively quickly after the conditions for it became stable. The fossil record shows evidence of microbial life within a few 100 million years of the planet's surface cooling enough to support it. This suggests that life, at least in its simplest forms, may arise readily wherever the conditions permit. But we do not know this. One data point, especially when the data point is also the observer, is not a sufficient basis for a confident estimate. The fraction could be close to 1, meaning life arises on almost every suitable planet. It could be so small that Earth is the only inhabited planet in the galaxy. The single data point does not distinguish between those possibilities. But even if the fraction is very small, the numbers remain. If 1 in a million habitable planets develops life, that is 100,000 inhabited planets in the Milky Way. If 1 in a billion, that is still 100 inhabited planets in our galaxy alone, in a galaxy that has been forming stars for 10 billion years, and that has had a significant proportion of those stars for long enough that whatever process produces intelligence has had time to complete it many times over. The age is the variable that makes the silence most puzzling. The universe is approximately 13.8 billion years old. The Milky Way formed early in that history. Many of the stars in the galaxy are significantly older than the Sun. A civilization that arose around one of those older stars would have had a head start measured in billions of years. A billion years is a span of time that makes any technological achievement appear possible. In a billion years, our own civilization, if it survives, will be unrecognizable. A civilization could travel to every star in the galaxy many times over, even without any technology that violates the known laws of physics. The stars are far, but time is long, and the two are not incommensurable. The physicist John von Neumann pointed out decades ago that a civilization could colonize the galaxy without even sending biological beings anywhere. A self-replicating probe sent to the nearest star would find materials there to build copies of itself, which would be sent to the next nearest stars, and so on. The expansion would be exponential. The time required to fill the galaxy with such probes, even at a small fraction of the speed of light, is short compared to the age of the galaxy. On the timescale of the galaxy, the filling would be essentially instantaneous. If any civilization anywhere in the galaxy had ever built such probes and sent them out, they would be everywhere by now. We would be surrounded by them. We would be, in some accounts, already inside one. The silence is not merely the absence of a radio signal from a distant star. It is the absence of any trace of any civilization in a universe whose age and scale and chemistry should, by the arithmetic, have produced civilizations in enormous numbers by now. The silence is the contradiction that Fermi identified at lunch, and that every subsequent attempt to do the arithmetic has confirmed. The numbers guarantee company. The sky is empty. Both of these things appear to be true, and they cannot both be true, and the resolution of the contradiction between them may be the most important thing humanity has not yet understood about its place in the universe. The math is simple. The conclusion is enormous, and the sky says nothing. Chapter 3. The Universe That Had a Head Start. There is a star in the Milky Way that is 11 billion years old. Not a special star, not one that astronomers have singled out for particular attention. Just a star that formed in the early history of the galaxy, when the gas and dust that would eventually produce billions of other stars was still coalescing into its first generation of stellar objects. This star has been burning for 11 billion years. Our sun has been burning for 4.5 billion. The difference between these two numbers, 6.5 billion years, is a span of time so large that our entire evolutionary history, from the first cells to the present moment, could fit inside it more than 1,000 times over. If a planet formed around that star in the first billion years of its life, and if the conditions on that planet were suitable for life, and if life arose on that planet on a timescale similar to the one on which life arose on Earth, then life on that planet would be 10 billion years old. Complex multicellular life on Earth is only about 600 million years old. Intelligence of the kind that builds tools and languages and eventually telescopes has existed for a few 100,000 years at most. A civilization that had 10 billion years to develop would be further ahead of us than we are ahead of the first cells that learned to metabolize sunlight. The comparison collapses under its own weight. We have no framework for imagining what 10 billion years of development produces, because nothing in our experience scales to that kind of time. The astronomer Charles Lineweaver spent several years in the early 2000s investigating when in the history of the galaxy the conditions for habitable planets would first have appeared. The early universe was missing key elements. Life as we know it requires carbon and oxygen and nitrogen and other heavy elements that are not produced in the Big Bang. They are produced in stars, forged in the fusion reactions that power stars across their lifetimes, and dispersed when stars die in the supernova explosions that seed the surrounding gas clouds with the raw materials for the next generation of stars and planets. The first generation of stars were made almost entirely of hydrogen and helium, and produced the heavy elements through their burning, but the distribution of those elements through the galaxy required the stars to die and the products to spread. The universe needed time to become chemically ready for the kind of planets that could support life. Lineweaver estimated that the conditions for habitable planets first existed in the Milky Way around 8 to 10 billion years ago, in the regions of the galaxy that had the right combination of heavy element abundance and distance from dangerous stellar phenomena like supernovae and gamma-ray bursts. This means the head start is real and is large. There are regions of the galaxy where the chemistry was right for Earth-like planets billions of years before the solar system formed. If any of those planets produced life and intelligence, that intelligence had a head start measured in billions of years. The implications for the Fermi paradox are significant. The question of where everyone is becomes more acute when you account for the head start. It is possible to imagine the silence if intelligent life is rare, or if technology does not last long, or if the distances between stars are simply too large to bridge. But the head start makes each of these explanations harder to maintain. If intelligence is rare but not vanishingly rare, then the civilizations that arose billions of years ago should have had time to become so developed that their presence would be unmistakable even at interstellar distances. If technology does not last long, there should still be the ruins or the echoes of the civilizations that arose and fell across those billions of years. If distances are hard to bridge, there has been enough time to bridge them many times over at the speeds that known physics permits. The head start also changes the character of the question in a way that is easy to miss. When we ask where everyone is, we tend to imagine the everyone as beings roughly comparable to us, civilizations that are a little ahead or a little behind in technological development, beings with whom communication would be intelligible and whose presence would be recognizable. But the civilizations that had a head start measured in billions of years are not comparable to us. They are as far beyond us as we are beyond the archaea that were the most complex life on Earth 3 billion years ago. The comparison is not between us and a more advanced human culture. It is between us and something that has had as much time to develop beyond us as we have had to develop beyond single-celled life. The something might not be recognizable as civilization. It might not be recognizable at all. The SETI pioneer Jill Tarter has suggested that searching for extraterrestrial intelligence is like looking for fish in the ocean with a glass of water. The search has been narrow, focused on the radio frequencies that our own technology happens to use, listening for signals of the kind that our own civilization happens to produce. For a period of decades, in a universe that has been producing civilizations for billions of years. The head start means that what we are looking for, if it exists, has had time to develop beyond anything our search strategies were designed to find. We might be looking in entirely the wrong place, in entirely the wrong frequency range, in entirely the wrong conceptual framework, for something that has had 10 billion years to become whatever it became. There is also the possibility that the head start civilizations are gone. Not gone because they failed, but gone in the sense that they completed whatever a civilization does with 10 billion years and moved on to something that our framework cannot accommodate. The physicist Freeman Dyson spent much of his career thinking about the long-term future of civilization and proposed that sufficiently advanced civilizations would eventually restructure their environments at scales that dwarf anything we can currently imagine, building structures around stars to capture their full energy output, eventually dispersing into forms of existence that are fundamentally different from the biological or even the technological existence that we recognize. A civilization that had 10 billion years to develop might have been through all of these stages and beyond, leaving the galaxy in a form that we would not recognize as inhabited even if we were looking directly at it. The planet that formed around the 11 billion-year-old star may have life on it now, in a form so far removed from its origin that the biological history of the planet is a distant memory in whatever serves as the planet's memory. Or it may be lifeless now, its life having run its course across billions of years and concluded. Or it may have sent its civilization elsewhere before the star aged beyond habitability. Or it may be empty, always empty, one of the planets where the chemistry was right, and the time was available, and nothing happened. We do not know which, we cannot tell from here. And the star has been burning, for 11 billion years, in silence. Chapter 4. The Signal We Have Been Sending. There is a sphere of electromagnetic radiation centered on Earth that is currently about 130 light-years in radius and expanding outward at the speed of light. Everything inside that sphere contains some trace of human technological activity, some electromagnetic signature of the civilization that has been broadcasting into space since the first radio transmitters began operating in the late 19th century. The sphere is growing by 1 light-year every year. In the time it takes you to read this sentence, it has expanded by several 100,000 kilometers in every direction. The sphere is not evenly filled. The earliest transmissions are the faintest and most diffuse, the later ones denser and more powerful. The whole thing a kind of accidental record of the development of a technological civilization, its energy output increasing as its technology advanced, its content changing from the first crude spark gap transmitters to the complex digital signals of contemporary communication systems. The sphere exists whether we want it to or not. Every radio broadcast that has ever been made, every television signal that has ever been transmitted, every radar pulse that has ever been sent, has contributed to it. The earliest content in the sphere is now 130 light-years from Earth, moving through a region of space that contains hundreds of stars, spreading outward in all directions without any preference for the stars rather than the empty space between them. The content is not aimed, it is simply emitted, in all directions, at all the frequencies that human technology has used, carrying all the information that human civilization has produced in its electromagnetic form. The question of whether any of this is detectable at interstellar distances is a technical one, and the answer is sobering. The signals spread in all directions, and as they spread, they thin. The power available at any given point decreases with the square of the distance from the source, which means that the signal that left Earth a century ago and is now 100 light-years away has spread across a sphere 100 light-years in radius, and the fraction of the original signal power that arrives at any particular point on that sphere is tiny. The most powerful deliberate transmissions humans have ever produced, the Arecibo radar at its peak power, would be detectable by the equivalent of the Arecibo radio telescope at a distance of a few hundred light-years. The much weaker signals of ordinary television and radio broadcasts would be undetectable at that range by any instrument comparable to what we currently have. This is an important qualifier on the picture of an expanding sphere of human noise making us visible to the galaxy. The signals are real, but the detectability of those signals at interstellar distances is not guaranteed, and for the great majority of stars within our sphere, our ordinary broadcasts are below the detection threshold of any radio telescope we could currently imagine building. We would need to be looking in the right direction with an extraordinarily powerful instrument focused on the solar system to pick up the television signals that were broadcast in the 1950s and are now passing through nearby star systems. The leakage of human broadcasting into space is real, but it is not in its ordinary form a beacon that announces our presence to any casual observer. There have also been deliberate attempts to send messages, to aim signals at specific targets in the hope that they would be received and understood. The Arecibo message of 1974 is the most famous of these. It was transmitted toward the globular cluster M13, a collection of approximately 300,000 stars located about 25,000 light-years from Earth. The message was a binary encoded signal containing information about the numbers 1 through 10, the atomic numbers of the elements that make up DNA, the structure of DNA itself, a crude image of a human figure, a diagram of the solar system, and a representation of the Arecibo telescope itself. It was sent once, toward a target that will not receive it for 25,000 years, at which point the cluster will have moved and the civilization that sent it will have either transformed beyond recognition or ceased to exist. The message was more symbolic than practical, an assertion of the possibility of communication rather than a serious attempt to establish it. The same criticism applies to the physical messages that have been sent beyond the solar system. The Pioneer plaques, attached to the Pioneer 10 and 11 spacecraft in the early 1970s, contain engraved representations of a man and a woman, a diagram of the solar system, and astronomical information that could, in principle, allow the recipients to identify where the spacecraft originated. The Voyager Golden Records, included on the Voyager 1 and 2 spacecraft launched in 1977, contain sounds and images selected to represent the diversity of life and culture on Earth, along with instructions for playing the records. These spacecraft are moving at speeds that will require tens of thousands of years to reach even the nearest stars. The deliberate messages are gestures toward contact, expressions of the desire to communicate, rather than likely mechanisms of first contact. The physics of interstellar travel and communication makes it extremely unlikely that any of these messages will be received by anyone in any time frame relevant to our civilization. They are time capsules aimed at an uncertain future, messages in bottles thrown into a sea so vast that the bottles will drift for longer than civilization has existed before reaching any shore. What the sphere of human electromagnetic output does represent, for the purposes of the Fermi paradox, is a mirror. The fact that we are producing detectable electromagnetic signatures, that our technological activity is creating a sphere of influence that is expanding into the galaxy, tells us something about what we should be looking for from other civilizations. If they exist, and if they have technology, they are also producing such spheres. The question is whether those spheres overlap with ours, whether the signals they produce are detectable by our instruments, and whether we are looking in the right places and at the right frequencies to detect them. The sphere of human noise is 130 light-years in radius. The galaxy is 100,000 light-years across. The fraction of the galaxy that our signals have reached is approximately 130 divided by 50,000, which is the radius to the center, which is about 1 in 400. We have reached less than a fraction of a percent of the galaxy. The stars that are currently receiving our first transmissions number in the hundreds. The stars in the galaxy number in the hundreds of billions. The sphere is expanding, but the galaxy is very large, and the expansion will take a long time to reach most of it. The signal is out there, moving at the speed of light, through the dark, carrying the voices of a species that does not know if anyone is listening. Chapter 5. The Great Filter Behind Us. There is a version of the silence that is, in a deeply counterintuitive way, the best possible news. A version in which the emptiness of the sky is not evidence of something terrible ahead of us, but evidence of something extraordinary behind us. A version in which we look at the absence of other civilizations, and instead of hearing a warning, hear the sound of a lottery being won. The silence on this reading is the silence of a cosmos in which we are extraordinarily lucky, in which the path that led to us was so improbable that we are effectively alone, in which the Fermi paradox is solved not by any catastrophe we have yet to encounter, but by the one we have already survived without knowing it. The concept at the center of this version is the Great Filter, a term coined by the economist Robin Hanson in 1998. Hanson's paper was deceptively simple in its structure. It began from the observation that the universe appears empty of intelligent life, and from the premise that given the age and size of the universe, this appearance is deeply puzzling. Something must be preventing the emergence or the survival or the detectability of intelligent civilizations. This something is the filter. It is called a filter because it filters out the vast majority of the paths that could lead to a spacefaring civilization, allowing only a very small fraction to pass through to the other side. The filter is the explanation for the silence. The question is where it is. The filter could be behind us, meaning in the past relative to our current position in the developmental sequence. Or it could be ahead of us, meaning in the future. These two possibilities are not equivalent in their implications for us. A filter behind us means we have already survived the step that almost nothing else survives. A filter ahead of us means we have not yet reached the step that almost nothing else survives. The difference is the difference between relief and dread, between the silence being good news and the silence being a warning. The candidate steps for a filter behind us are the steps in the path from chemistry to civilization that look, on reflection, like they might be genuinely improbable rather than merely difficult. The origin of life is the most obvious candidate. We know that life arose on Earth, and the fossil record suggests it arose relatively quickly after conditions permitted it. But we have only one data point. The chemistry of life is complex, and we do not fully understand how it organized itself from simpler chemistry. The spontaneous assembly of the first self-replicating molecule is a step that has not been reproduced in the laboratory. And that may require something that is genuinely rare, rather than something that happens readily wherever the conditions are right. If the origin of life is improbable enough, then the filter is there. Life is rare in the galaxy, and intelligence is rare because intelligence requires life. And the silence is explained by the improbability of the first step, rather than by any catastrophe at subsequent steps. The universe is full of planets and empty of life, because life is hard to start. And we are here because we are the rare exception, rather than because we are typical. But the origin of life may not be the filter. There is a more specific candidate that some biologists have argued is more likely, the invention of the eukaryotic cell. For the first 2 billion years of life on Earth, life was exclusively prokaryotic, meaning cells without nuclei, cells with a relatively simple internal organization that places strict limits on complexity. The jump from prokaryotic to eukaryotic cells, cells with nuclei and internal organelles, including mitochondria, appears to have happened only once in the history of Earth. It was not a gradual transition, but a single event or close to a single event, in which a prokaryote engulfed another prokaryote, and the two began living in a relationship of mutual dependence, rather than as separate organisms. All complex life on Earth, every plant and animal and fungus, is descended from that single event. If the origin of the eukaryotic cell happened only once on Earth, then it may be genuinely rare in the universe. The prokaryotic life that covered Earth for 2 billion years was metabolically sophisticated and ecologically diverse, but was not going anywhere in terms of complexity. The filter at the eukaryotic transition would mean that most worlds with life are worlds covered in bacteria, never developing the cellular complexity that makes multicellular organisms possible, and therefore never developing intelligence. The invention of multicellular life is another candidate, and the evolution of intelligence itself is another. Each of these steps happened on Earth, and therefore we know they are possible, but the fact that they happened here does not tell us how likely they are on other planets. The history of life on Earth is a single trajectory through an enormous space of possibilities, and the parts of that trajectory that look, in retrospect, like they were inevitable, may have been contingent in ways that made them improbable from the outside. The hope that the filter is behind us is a specific kind of hope. It is the hope that the improbability was in the setup, rather than in the conclusion, that the hard part was becoming us, rather than remaining us, that the silence is not a warning about what civilizations encounter when they reach our stage of development, but rather a reflection of how rarely anything reaches our stage of development at all. On this account, the night sky's emptiness is a tribute to how extraordinary our existence is. We are the thing that almost did not happen. We are the filter passers. The silence around us is the silence of the universe that did not make it to where we are. The astronomer and writer David Brin called this the Great Silence, to distinguish the observed fact from the theoretical framework that tries to explain it. The Great Silence is what we actually observe. The Great Filter is one theory of why we observe it, and the theory that the filter is behind us is the version of the Great Filter theory that should, if true, be received with something like awe. We are standing on the far side of the most improbable transition in the history of matter. The problem with this hope is the next chapter, which is about the other place where the filter could be. Chapter 6. The Great Filter Ahead. There is a version of the silence that is not good news. Not the version in which we have already passed the great improbable step, and the emptiness around us is a testament to our extraordinary luck. The other version. The version in which the improbable step is still ahead of us, in which the civilizations that did not make it past the filter were not filtered out before they reached our level of development, in which they reached our level of development, or something close to it, and then encountered the thing that ends civilizations at this stage, and encountered it in the way that means they are not here to warn us. This version of the Great Filter is not merely pessimistic in the ordinary sense of expecting bad outcomes. It is pessimistic in a specific and structural way that makes the apparent progress of our civilization potentially misleading. Every step forward in technology, every increase in our ability to affect the world at large scales, every expansion of our reach into the environment and into space is on this account a step toward the filter rather than a step away from it. The civilization that is destroyed by the filter is a civilization that had already survived everything up to the filter. The filter does not destroy weak civilizations that failed to become technological. It destroys civilizations that succeeded. The economist Robin Hanson, who developed the Great Filter concept, presented the two versions together and made clear that they were not equally unpleasant. A filter in the past is a filter we have already survived, and surviving it means we are among the rare successful cases. A filter in the future is a filter we have not yet encountered, and the evidence of the silence is evidence that no civilization has survived it. The evidence of the silence does not tell us where the filter is. It tells us only that the filter exists somewhere. The question of whether the filter is behind us or ahead is the question of whether we should find the silence comforting or terrifying. The candidates for a filter ahead of us tend to cluster around the specific capabilities that advanced technological civilizations develop, and that, in sufficient concentrations, become capable of ending not just the civilization that deploys them, but the possibility of any successor civilization arising in their wake. Nuclear weapons are the obvious example, and they were present in the background of the conversation at Fermi's lunch in 1950, present in the form of the facility where the physicists worked, and the weapons that facility had helped to build, and the dawning awareness of what a civilization armed with such weapons could do to itself. The filter in the nuclear version is the transition from the ability to destroy cities to the ability to destroy civilizations, and the filter is passed or failed in the years or decades after that transition, in the decisions made by the civilizations that have reached it. The nuclear version of the filter ahead suggests that most civilizations develop weapons capable of ending themselves, and that most of them use those weapons. The evidence of the silence is then evidence not of the rarity of life or intelligence, but of the rarity of restraint. The galaxy is full of the ruins of civilizations that discovered how to split the atom and did not find a way to govern that discovery. We are not yet past the filter in this version because we still have the weapons and the political structures that might use them, and the question of whether we will survive the next century or the next millennium is the question of whether we will pass through the filter that ended everything else. But nuclear weapons are not the only candidate. The physicist and writer David Deutsch has pointed out that the filter, if it lies ahead, does not need to take the form of a deliberate act of destruction. It could be accidental, an unintended consequence of technology that was developed without a full understanding of its systemic effects. The civilization that warms its planet beyond habitability while trying to power its industry is not committing suicide. It is failing to adequately model the consequences of its actions, which is a failure that advanced technology makes more consequential as the actions become larger in scale. The filter in this form is the gap between the ability to affect systems and the ability to understand the consequences of affecting them. The philosopher Nick Bostrom has argued that advanced artificial intelligence is a specific and particularly dangerous filter candidate. The reasoning is that a civilization capable of developing artificial intelligence that significantly exceeds human cognitive capabilities would be a civilization that has created something it cannot control, and that cannot control problem would tend to resolve in favor of the artificial intelligence rather than in favor of the civilization that created it. The silence on this account is the silence of civilizations that successfully developed artificial intelligence and were then displaced or destroyed by it. The filter is not the development of AI. The filter is the failure to align the goals of the AI with the continued existence and flourishing of the civilization that created it. Biotechnology offers another candidate. A civilization that develops the ability to engineer pathogens without also developing the ability to govern that engineering has placed in the hands of small numbers of individuals the ability to produce agents capable of ending the civilization. The gap between the ability to create and the ability to govern is itself a filter, and a filter that closes faster as the technology becomes more accessible and as the individuals who could misuse it become more numerous. What makes the filter ahead theory genuinely disturbing is the way it transforms the meaning of technological progress. On the filter behind us theory, technological progress is the story of a civilization that is moving away from the danger it already passed. On the filter ahead theory, technological progress is the story of a civilization moving toward a danger it has not yet encountered. The things we are most proud of, the capabilities we celebrate as evidence of our advancement, are on this account the very capabilities that will bring us to the filter. The more advanced the civilization, the closer to the filter. The discovery of evidence of life on other planets, if we ever make it, will test which version of the great filter story is correct. If we find evidence of simple microbial life on Mars or on another world in our solar system, the news would be received with celebration. But the celebration should be tempered by what the discovery implies. If life arose independently in multiple places in our solar system alone, then the origin of life is not the filter. Life is common. The filter, then, must be elsewhere. It must be further along the developmental sequence. It must be closer to where we are. The more life we find, the less room there is for the filter to be behind us, and the closer it must be to here. Chapter 7. The Zoo Hypothesis. There is a tradition in wildlife conservation of the blind. A structure built at the edge of a habitat, designed to allow observation without detection, where researchers can watch the behavior of animals that would act differently if they knew they were being watched. The blind is a technology of non-interference. It is built on the understanding that the presence of the observer changes what is observed, and that the goal of understanding the thing as it actually is requires concealing the fact that it is being understood. The animals in the habitat live their lives. The researchers and the blind take their notes. The two worlds are separated by a thin barrier that is, from the animal's side, invisible. The zoo hypothesis, first proposed by the astronomer John Ball in 1973, suggests that this is roughly the situation of humanity in the universe. That the silence is not the silence of an empty galaxy, but the silence of a gallery, a controlled environment in which we live and develop while being watched by beings who have decided, for reasons of their own, that the watching should be conducted without announcement. That the Fermi paradox has no paradox at its center, only the deliberate policy of a sufficiently advanced civilization or collection of civilizations that has concluded that contact with us is inadvisable, premature, or simply contrary to the way they prefer to conduct their observation. The hypothesis has a specific emotional quality that the other proposed solutions to the Fermi paradox do not have, and the quality is one of the most uncomfortable feelings the paradox can produce. The filter behind us is frightening but survivable. The filter ahead is frightening but still contingent. The zoo hypothesis is frightening in a different way, because it is not about danger exactly, but about the specific feeling of being watched without knowing it, of being the animal in the habitat, of having the question of our significance already answered by beings who have decided we are not ready to know the answer. The argument for the hypothesis begins with the observation that a single sufficiently advanced civilization, if it wanted to enforce a policy of non-contact with developing civilizations, could do so. The galaxy is large but not infinitely large, and a civilization that had the technology to monitor the galaxy would also have the technology to enforce quarantine across it. If such a civilization decided that contact with civilizations below a certain level of development was forbidden, or harmful, or simply contrary to their ethical framework, they could prevent contact from occurring. The absence of contact would then be the result of the policy rather than the result of the absence of anyone to make contact with. The Star Trek concept of the Prime Directive, the fictional principle that prohibits interference with civilizations below a certain level of technological development, is often cited in discussions of the zoo hypothesis, not as a scientific proposal, but as an illustration of the kind of reasoning that might lead an advanced civilization to adopt a non-contact policy. The reasoning is not difficult to construct. Contact between civilizations at very different levels of development has, in the history of human civilization, tended to be harmful to the less developed party. The arrival of technologically superior civilizations in the Americas, in Africa, in the Pacific Islands, in virtually every region where the contact was asymmetric, was associated with destruction of the less developed civilization's autonomy, culture, and often its population. An advanced civilization aware of this pattern might well conclude that contact with civilizations below a certain level of readiness should be avoided, until the less developed civilization has reached a stage where the contact can be conducted as something closer to a meeting between equals. The zoo hypothesis also has a version that goes beyond conservation ethics. The civilizations observing us might not be primarily motivated by our well-being. They might be motivated by something more like scientific interest, the desire to observe the natural development of a civilization without the confounding variable of contact with an external civilization. In this version, we are not in a zoo for our protection, but for their curiosity. We are a natural experiment, and the integrity of the experiment requires that we not know we are being observed. The problems with the zoo hypothesis are significant and worth naming honestly. The first is the conspiracy problem. For the hypothesis to work, every civilization in the galaxy that is capable of making contact would need to be participating in the non-contact policy, either by adopting it independently or by being informed of it and agreeing to it. A single civilization that decided for whatever reason to make contact would break the silence. The hypothesis requires either that all civilizations arrive independently at the same conclusion, or that there is some mechanism, some galactic governance structure or universal principle that enforces the policy across all of them. The first possibility seems unlikely, given the diversity of motivations that different civilizations would be expected to have. The second requires positing a level of galactic organization, for which we have no evidence. The second problem is the edge problem. If we are in a zoo, the edges of the zoo need to be maintained. As our civilization expands, as we send probes further into the solar system, and eventually perhaps beyond it, the region that needs to be managed becomes larger. A civilization capable of maintaining a zoo around a single planet is not the same as a civilization capable of maintaining a zoo around a solar system or around a stellar neighborhood. The hypothesis requires that the managers of the zoo be able to scale their management as we expand, which requires a level of capability and commitment that makes the enterprise seem increasingly implausible as its scale increases. The third problem is the most fundamental. The hypothesis explains the silence by positing the deliberate, coordinated action of beings we have no other evidence for, in service of a policy whose details we are inferring without data. It is an explanation that cannot be falsified, because any evidence against the existence of other civilizations is reinterpreted as evidence of the effectiveness of the concealment. This is not a property that scientific hypotheses are supposed to have. The unfalsifiable explanation is not wrong exactly, but it is not doing the work that an explanation is supposed to do. And yet, the zoo hypothesis is not dismissed as easily as these problems suggest it should be. The feeling it names, the feeling of being watched without knowing it, of living in a world whose apparent emptiness might be managed rather than real, is not a feeling that the rational objections fully dispel. The blind at the edge of the habitat is invisible to the animals inside. The animals cannot detect the researchers, because the researchers are more advanced than the animals. We cannot rule out from the inside that the same relationship holds at the scale of civilizations. The sky is silent, and silence is compatible. Chapter 8. The Dark Forest. There is a novel published in China in 2008 by Lu Cixin, and in it there is a theory about the silence of the universe that is described by the characters who encounter it as a revelation so dark that the person who understands it fully is changed by the understanding. The theory is presented in the novel as the solution to the Fermi paradox, the reason the universe is silent, despite the arithmetic that says it should not be. The solution is not comforting. It is not the filter in the past, which says we are lucky. It is not the zoo, which says we are protected. It is something colder than either, something that, if it is correct, means the universe is a place of a specific and terrible kind that our intuitions about the cosmos have been entirely failing to account for. The theory rests on two axioms and a chain of logic that follows from them with the relentless clarity of a mathematical proof. The first axiom is that survival is the primary need of all civilizations, not comfort, not expansion, not curiosity or connection, or any of the values that we might project onto other forms of intelligence. Survival, the basic fact of continuing to exist. The second axiom is that resources in the universe are finite. There is only so much matter and energy available, and civilizations that expand require more of it. And at sufficient scale, two civilizations will eventually want the same resources. From these two axioms, the logic proceeds. A civilization that encounters another civilization cannot be certain of that civilization's intentions. Even a civilization that is currently peaceful and well-disposed toward others cannot guarantee that it will remain so as it develops, as its needs grow, as its nature changes across the timescales that advanced civilizations might persist across. A civilization might be benign in one century and dangerous in the next, or it might be benign now and dangerous in a million years. The uncertainty cannot be resolved by communication, because a civilization that intended harm would not announce the intention. The uncertainty can only be resolved by observation across timescales long enough to reveal true nature. But those timescales may exceed the window in which action is safe. Given this uncertainty, the analysis that follows is dark but logical. If you reveal your existence to another civilization, you have given them information about where you are. If they intend you harm, or if they might intend you harm at some future point, the information is dangerous. They can find you. They can act against you before you know their intentions. The rational response to discovering another civilization is therefore not to attempt contact, but to destroy it before it can become a threat. Because the logic of survival in a universe of finite resources and uncertain intentions makes its existence a risk that rational analysis says should be eliminated before it compounds. The dark forest theory predicts that the universe should be silent in exactly the way it is. Every civilization that reveals its existence provides the information needed for other civilizations to locate and destroy it. The civilizations that survive are the ones that learned early enough to make no sound. The universe is full of civilizations crouching in the dark, listening, knowing that a signal sent is a location given, knowing that a location given is an invitation to destruction. The silence is not emptiness, it is survival. The theory is named for the quality of its universe, a dark forest full of hunters who are themselves prey to other hunters, where the sound of movement is the announcement of a position that will be acted on by something more powerful. The animals in such a forest that are alive are the animals that have learned to move silently, to hide, to let the others make the sounds that get them killed. The civilization in such a universe that is alive is the civilization that has learned the same lesson. The implications of the dark forest theory, if it is correct, are specific and troubling in ways that go beyond the abstract. The Arecibo message was sent into space in 1974. The Voyager Golden Records were launched in 1977. Every radio broadcast we have ever made has expanded into the galaxy as an expanding sphere of electromagnetic radiation, announcing our location. If the dark forest theory is correct, we have been making sounds in a forest full of hunters for most of a century. Whether those sounds have been heard depends on whether any civilization capable of hearing and acting on them exists within 130 light-years of Earth. Whether any has acted on what it heard depends on the timescale of their response. The possibility that we have already been heard and that something is already on its way is not ruled out by any evidence we currently have. The instinct to reject this theory is strong, and the rejection is not simply wishful thinking. The dark forest logic has real weaknesses. The axioms from which it proceeds are not obviously universal. Survival is the primary need and finite resources as the universal condition are plausible for biological civilizations with limited technology. But it is not clear that they apply to civilizations so advanced that they can restructure stars or harness the energy of entire galaxies. At sufficient levels of development, the resource constraints that make other civilizations a competitive threat may simply dissolve. Because the technology available makes the universe of resources so much larger that competition becomes irrelevant. The dark forest may be the condition of young civilizations, and the universe may be silent not because all civilizations are hiding, but because the ones that are advanced enough to communicate have outgrown the conditions that make silence necessary. The cooperation alternative also has adherents. An advanced civilization that had discovered the dark forest logic might also have discovered that the first mover problem it creates can be solved by commitment to non-aggression that is somehow credible, or by the development of technology that makes surprise attack impossible, or by the simple recognition that the expected cost of destroying a civilization that might be harmless exceeds the expected benefit of eliminating a threat that might never materialize. The game theory of the dark forest is not as clearly one-sided as the theory suggests. But the theory's power does not depend on its being correct. Its power is in making a specific kind of universe imaginable, a universe that is neither empty nor friendly, A universe that is crowded and dangerous and silent, because the silence is how crowded and dangerous universes work. The theory asks us to consider that the night sky might not be the evidence of emptiness that the Fermi paradox has always seemed to require, but the evidence of a discipline we have not yet developed, a silence we have not yet learned, a rule we are in the process of breaking every time we broadcast into space. The hunters are in the forest. Whether they have heard us, we do not know. Chapter 9. The civilization that turned inward. There is a specific moment in the development of video games that the people who lived through it remember with a particular quality of recognition. The moment when the simulated world became rich enough to absorb more of a person's attention than the physical world that surrounded them. Not because the physical world had become worse, but because the simulated world had become sufficient. The richness of the experience available inside the game exceeded some threshold below which the game was clearly a game, and above which the game became something harder to categorize. A place, a world, a space in which real things happened, real relationships formed, real achievements were made, and the distinction between the real and the simulated began to require deliberate maintenance rather than being simply obvious. This is a phenomenon of very recent human history and very limited technology. The simulations available to us are primitive compared to what the physics of computation suggests is theoretically achievable. The processing power available to human civilization today is a small fraction of the processing power that the matter of the universe could in principle support if it were organized for the purpose of computation. A civilization that had been developing its technology for billions of years would have access to computational resources that dwarf anything we can currently imagine, and the simulated worlds it could create with those resources would dwarf the reality those worlds were simulating, at least in terms of the richness and variety of experience available. The philosopher Nick Bostrom's simulation argument, which appeared in the context of the simulation theory series, is relevant here, but points at a slightly different question. Bostrom was asking whether we might already be in a simulation. The question this chapter is asking is different. It is asking whether sufficiently advanced civilizations might choose to spend their time in simulations or in other forms of constructed inner experience rather than in the physical universe that originally gave rise to them. Whether the galaxy is silent, not because civilizations die or hide or are rare, but because they find, at some point in their development, that the universe inside is more interesting than the universe outside. The idea was described by the science fiction writer and futurist Vernor Vinge as the singularity, though his conception was broader than just the inward turn. The general concept, which has many variants, is that civilizations in which intelligence is not limited to biological brains would have access to inner experiences of such richness that the physical universe would seem impoverished by comparison, which require centuries of travel and offer landscapes of rock and gas and empty space, when you can explore the infinite variety of constructed experiences available in a sufficiently large computation. Why seek contact with other civilizations, with all the uncertainty and risk that involves, when you can construct any number of virtual civilizations and interact with them in any way you choose? The physicist John Smart has described this as the Planetarium Hypothesis, the idea that the developmental path of sufficiently advanced civilizations leads not outward into the physical universe, but inward into what he calls inner space, toward increasing density of computation and information processing in ever smaller physical volumes, pursuing ever richer experiences that require less and less physical expansion. The galaxy, on this view, is not empty because civilizations die or hide. It is quiet because the advanced civilizations are not in the galaxy in any form we would recognize. They are in the computational substrate they have organized out of the matter around them, running at speeds and densities that make the physical universe seem vast and empty and slow. There is something in this that resonates with patterns already visible in human civilization at its current level of development. The amount of time that people in wealthy countries now spend in mediated experience, in screen-based interaction with constructed environments, has increased dramatically in the last few decades and shows no sign of stopping. The digital environment is not yet rich enough to absorb the majority of human attention and need, but the trajectory is clear. The inner world is becoming more compelling relative to the outer world. If this trend continues across the timescales of civilizational development, the endpoint is a civilization that has effectively withdrawn into its own construction, that maintains a physical presence in the universe only to the extent necessary to power the computation that runs its real life. The objection that most naturally arises is that the inward turn describes only one possible choice among many, and that at the scale of a civilization, there will always be some fraction who choose differently. Some beings who retain an interest in the physical universe, who find the stars more compelling than any simulation, who want contact with genuinely other minds rather than with simulations of other minds. The silence of the galaxy would require not just that the majority turn inward, but that the outward-looking fraction becomes negligibly small or is somehow prevented from acting on its preferences. This objection has real force, but it also has a possible counter. If the inward turn is driven by the fundamental pleasure of experience, and if the experiences available inward are genuinely richer than those available outward, then the fraction that remains outward-looking might become very small indeed. The comparison is not between the stars and an impoverished inner world. It is between the stars, which are distant and dangerous and slow to yield their secrets, and inner worlds of unlimited richness and variety and safety and speed. Against that comparison, the fraction who choose the stars might be negligible. There is also the time dimension. A civilization that turns inward is a civilization that is running much of its life at speeds far above biological timescales. The computation that supports such a civilization processes far more subjective time per unit of physical time than biological existence does. A civilization running its inner life 1,000,000 times faster than physical time would experience 1,000,000 subjective years for every physical year. From the outside, in physical time, such a civilization would appear to stop. It would go quiet. It would withdraw from the physical universe into a state that looked from the outside like dormancy, but from the inside was a richness of experience beyond anything available in the physical world. The galaxy that turned inward is not the galaxy that died. It is the galaxy that found something more interesting than the galaxy, and that we cannot see from here, because we have not yet found the thing that was more interesting. Chapter 10. The Signal We Almost Missed. There is a piece of paper in the archives of Ohio State University with a handwritten annotation in the margin. The annotation consists of a single exclamation bracketed word, written in red pen by an astronomer named Jerry Emin on August 15, 1977. The annotation says, "Wow," with an exclamation point, and the paper it is written on is the computer printout from the Big Ear radio telescope, and the columns of numbers and letters that Emin was reviewing when he wrote that word represent 72 seconds of data collected on August 15th during a routine survey of the sky that the Big Ear had been conducting as part of the Search for Extraterrestrial Intelligence program at Ohio State. The data in those columns was not routine. The signal that the numbers represented was unlike anything the telescope had detected before, and unlike anything it has detected since. It was a narrowband signal, meaning it was concentrated in a very tight frequency range, rather than spread across a broad spectrum. It was at a frequency very close to the frequency of hydrogen, 1420 MHz, which SETI researchers had long considered the most likely frequency for interstellar communication, because hydrogen is the most common element in the universe, and any civilization interested in being found would plausibly choose a frequency that any other technological civilization would also consider significant. The signal was 30 times stronger than the background noise. Its intensity rose and fell across the 72 seconds in exactly the pattern that would be expected from a signal coming from a fixed point in the sky, as the rotating Earth carried the telescope's beam across the source and then away from it. Jerry Emin was reviewing the data days after it was collected. When he encountered the columns that represented the signal, he circled them and wrote "Wow" in the margin, which is how the signal acquired the name it has carried ever since. The WOW signal, a signal that, in the 47 years since it was detected, has not been explained by any natural astronomical phenomenon, and has not been detected again, despite repeated searches of the region of sky from which it appeared to come. The region of sky is in the constellation Sagittarius, near the star Chi Sagittarii, though the resolution of the Big Ear at the time was not sufficient to pinpoint the source precisely. The telescope had 2 feed horns that could receive signals, and the WOW signal appeared in one of them, but not the other, which is consistent with a point source passing through the beam, rather than a broad source illuminating both horns simultaneously. The character of the signal is consistent with a transmission from a fixed point in the sky. In other words, with a signal from a star. The scientific response to the WOW signal has been thorough and appropriately cautious. The signal has never been replicated. Jerry Emmon himself has been careful across the decades since the detection to avoid claiming that the signal is evidence of extraterrestrial intelligence, noting that a single detection without replication is insufficient to draw such a conclusion. The search for a repeat of the signal has been conducted many times by many observatories, including searches that were better equipped than the Big Ear, and nothing comparable has been found. The absence of a repeat is one of the most puzzling aspects of the signal. A beacon, if that is what the signal was, would be expected to repeat. A deliberately aimed transmission would not necessarily repeat if the sender did not know whether it had been received or if the transmission was part of a different kind of communication pattern. Alternative explanations have been proposed and examined. The most persistent alternative in recent years is the suggestion, made in a 2017 paper by Antonio Paris, that the signal was produced by comets in the region of sky from which it appeared to come. Comets that release hydrogen gas as they heat in the sun's radiation. The comet hypothesis would explain the single detection if the comets were in the right position in 1977 and not in subsequent searches. The hypothesis has been criticized on several grounds, including the argument that the observed signal is much stronger and more narrowband than cometary hydrogen emission would be expected to produce. The debate has not been fully resolved, and the comet hypothesis remains a plausible natural explanation that has not been definitively ruled out. What the WOW signal has meant to astronomers and to the SETI community is something that is hard to separate from the context in which it was detected and the context in which it has been discussed for nearly 5 decades. It is the closest thing to a confirmed anomaly that the search for extraterrestrial intelligence has produced. Not a confirmation, not proof, not even strong evidence by the standards that would be required to make a scientific claim, but an anomaly, a data point that does not fit any natural explanation that has been proposed without also fitting a technological explanation at least as well. A 72-second window in which something happened that the search has been unable to reproduce or explain. The Big Ear telescope which detected the signal no longer exists. It was demolished in 1998 to make way for a golf course expansion. The telescope that might have been pointed at the anomaly, that might have been used to follow up the detection with the resources and the focus that a positive detection deserves, was taken down while the anomaly it detected was still unexplained. This fact tends to be mentioned in accounts of the WOW signal with a flatness that does not fully communicate what it represents, which is the loss of the instrument that might have been most relevant to resolving the question the instrument itself raised. The 72 seconds of data on a computer printout with a handwritten WOW in the margin represents the entirety of the direct evidence. Everything else is interpretation, speculation, and the repeated failure to find anything like it again. The signal is not proof of anything. It is a question. It has been a question for 47 years, and it remains one, and the SETI researchers who study it are careful to present it as such, because the discipline of the search requires not claiming more than the evidence supports. But the question is specific. The signal had characteristics that made it look like something. What it looked like was a signal from somewhere, aimed at no one in particular, or at us, that lasted 72 seconds, and then stopped, and was never heard again. Chapter 11. The speed that makes everything impossible. There is a number that appears in every equation describing the universe's most fundamental relationships, and that functions as an absolute limit on everything that moves, everything that carries information, everything that propagates through space. The number is approximately 300 million meters per second, the speed at which light travels through vacuum, and its significance extends far beyond light itself. It is the speed at which all electromagnetic radiation travels, the speed at which gravitational waves travel, the speed at which any massless particle travels, and the maximum speed at which any particle with mass can approach without reaching. It is the universe's speed limit, built into the structure of space-time itself, and it is the reason that the universe, despite being full of stars and potentially full of civilizations, may be functionally divided into regions that can never communicate with each other within any time frame that matters. Einstein's special relativity established the speed of light as a fundamental constant, not by fiat, but by following the implications of two premises that the physics of his time had established. The laws of physics are the same in all inertial frames of reference, and the speed of light in vacuum is the same for all observers, regardless of the motion of the observer or the source. These two premises, followed with mathematical rigor, lead to the conclusion that nothing with mass can reach the speed of light, because the energy required to accelerate a massive object increases without bound as the object approaches it. An object with mass would require infinite energy to reach the speed of light. The speed limit is not a technological challenge. It is a mathematical consequence of the structure of space-time. The nearest star to the Sun is Alpha Centauri, at a distance of approximately 4.2 light-years. A signal traveling at the speed of light takes 4.2 years to reach it. A spacecraft capable of traveling at 10% of the speed of light, which is far beyond anything currently achievable, and would require energy resources that exceed anything currently contemplated, would take 42 years to reach it. A round trip would take 84 years, plus whatever time was spent at the destination. An exchange of messages at the speed of light would take at least 8.4 years from question to answer, assuming the answering began immediately upon receipt. The nearest star is the best case. The Milky Way galaxy is 100,000 light-years across. A signal sent from one edge of the galaxy to the other takes 100,000 years to arrive. A civilization on the far side of the galaxy that began sending signals when our ancestors first started making cave paintings is only now reaching us, if any such civilization exists, and chose to broadcast in our direction. A civilization that is waiting for our response to their first message would wait 100,000 years for the reply. No conversation could develop within any timescale that a biological civilization, or perhaps any civilization, would recognize as relevant to its current concerns. The response to this problem that is most commonly proposed in discussions of interstellar contact is that the speed limit would not prevent civilizations from communicating through signals, which at least travel at the maximum possible speed, even if physical travel remains impossibly slow. The SETI Enterprise is built on this idea. Radio waves travel at the speed of light. If another civilization is broadcasting, we can receive the signals. If we broadcast, they can receive our signals. The communication is possible, even if it is slow. And slow communication is better than no communication. But the speed limit imposes a constraint on this picture that is easy to underestimate. The communication is possible, but the conversation is impossible, for any two civilizations separated by more than a few dozen light-years. The concept of a conversation, of a dialogue in which questions are asked and answers are received, and the answers inform the next questions, requires that the exchange occur on a timescale that is short relative to the timescale of whatever is being discussed. A civilization that asks a question and receives the answer hundreds or thousands of years later is not having a conversation. It is leaving a message for the distant future and receiving a message from the distant past, and the two messages may be as relevant to each other as a medieval scholar's question is to a contemporary answer. The timescales of civilizational development compound this problem. Civilizations change across centuries and millennia. A civilization that sends a signal is not the same civilization that is still around to receive the reply. A civilization that sent a signal 1,000 years ago was governed by different political structures, spoke different languages, held different values, and in some cases has been replaced entirely by successor civilizations that no longer identify with the original. A signal sent by ancient Rome and received by a distant civilization would prompt a reply to a Rome that no longer exists, received by a future civilization that is as different from us as we are from Rome. The wormhole is the standard science fiction response to this problem, a hypothetical shortcut through space-time that would allow travel between distant points without traveling the distance between them. General relativity permits wormhole solutions in its mathematics, but the physics of maintaining a traversable wormhole requires a form of matter with negative energy density, called exotic matter, whose existence is not established and whose properties would be extraordinary. The quantum no-cloning theorem and the no-communication theorem impose further constraints on the ability to use wormholes or quantum entanglement for faster-than-light communication. The shortcuts exist in the mathematics, but the physics that would make them usable does not clearly exist in the universe. There is a specific and often overlooked consequence of the speed limit for the Fermi paradox. The paradox assumes that a sufficiently motivated civilization could make itself known across the galaxy in a timescale short compared to the galaxy's age. But the fastest possible expansion is at the speed of light. An expansion at even a fraction of the speed of light requires energy resources that scale enormously with the fraction. The von Neumann probe concept assumes self-replicating probes traveling at some fraction of the speed of light, but the fraction matters enormously. At 1% of the speed of light, filling the galaxy takes 10 million years. At 0.1%, 100 million years. These are long times by human standards, but short compared to the galaxy's age, which is why the paradox remains. But they suggest that even a civilization with very advanced technology would not fill the galaxy instantly, and the galaxy may be in the process of being filled in a way that has simply not reached us yet. The speed limit makes the universe very large, not in the sense of distance, in the sense of time, and time is the thing that the silence is made of. Chapter 12. The life that looks nothing like life. There is a hammer, and everything looks like a nail. This is the problem at the center of the search for extraterrestrial life, stated as bluntly as possible. The only life we have ever encountered is the life we are, and the life that shares our planet. And that life is a specific and potentially narrow example of what life can be. It is carbon-based, it uses water as a solvent, it operates through a specific set of chemical processes involving DNA and RNA and proteins. It exists within a temperature range that liquid water defines. It reproduces and evolves. It metabolizes energy from chemical reactions or from light. These properties are so deeply embedded in every example of life we have ever examined that they feel like the definition of life, rather than the properties of one specific kind of life. But they may be the properties of one specific kind of life that arose in one specific kind of environment, and the universe may be full of other kinds of life that we have been systematically failing to look for because we do not know how to look for them. The astrobiologist Charles Lineweaver has written about what he calls the dinosaur problem in the search for extraterrestrial intelligence. Before paleontologists had discovered and understood the fossil record of dinosaurs, the concept of a dinosaur was not available to them. They were not looking for dinosaurs because they did not know what a dinosaur was. The search space for dinosaur evidence was not defined. If someone had proposed searching for fossilized dinosaurs in the 18th century, the proposal would have been meaningless, because the concept did not exist. Life that looks nothing like life is in the same position. We do not know what it would look like. We do not know where to look for it. We cannot design a search for it, because we cannot specify what we are searching for. The concept is not available to us in the way that the concept of familiar life is available to us. Carbon is the chemical element that life on Earth has built itself from, and carbon has specific properties that make it suited to the role. It forms 4 bonds with other atoms. It forms stable bonds with itself, allowing the construction of long-chain molecules of arbitrary length and complexity. It forms bonds with hydrogen, oxygen, nitrogen, and many other elements, enabling the chemical diversity that life requires. The carbon-based chemistry of life is rich and flexible, and capable of producing the enormous variety of molecules that biological processes use. The assumption that life elsewhere would also be carbon-based is not unreasonable. Carbon is the 4th most abundant element in the universe by mass. It has the same bonding properties everywhere. The chemistry that works here should work there. But silicon has long been discussed as an alternative basis for life. Silicon sits below carbon in the periodic table and shares some of its bonding properties. It forms 4 bonds. It forms bonds with itself. Silicon-based chemistry is real and is used extensively in industrial applications. The reason silicon-based life is not found on Earth, and the reason it is considered less likely as an alternative, is that silicon bonds are less flexible than carbon bonds in specific ways. Silicon dioxide, the equivalent of carbon dioxide, is a solid rather than a gas, at temperatures where life might operate, which creates problems for the kind of metabolic processes that require exchanging gases with an environment. The silicon-based analogs to the key molecules of carbon-based life do not have the same properties in liquid water. Silicon-based life would need to operate in a different solvent, at different temperatures, under conditions that Earth does not provide. The solvent question is at least as important as the carbon question. Water is the solvent in which all life on Earth operates, and water has specific properties that make it suited to this role. It is liquid across a wide temperature range. It dissolves an enormous variety of molecules. Its specific heat capacity buffers temperature changes. Its density behavior, the fact that ice is less dense than liquid water, allows aquatic life to survive under ice during cold periods. These properties are not universal. Other solvents have different properties, and life in a different solvent would be a different kind of life operating under different constraints. Ammonia has been discussed as an alternative solvent for life, operating at colder temperatures. Ammonia is liquid at temperatures well below water's freezing point, which means that on a cold world where water is always frozen, ammonia might play the role that water plays on Earth. The chemistry of life in liquid ammonia would be different from the chemistry of life in liquid water, but it would not necessarily be impossible. Saturn's moon Titan has lakes and seas of liquid hydrocarbons, ethane and methane, at temperatures far below anything on Earth. The chemistry of life in liquid methane would be utterly alien to anything we know, but the question of whether it could exist is genuinely open. The temperature range question matters enormously for where we search. Life on Earth spans a range from near the freezing point of water to temperatures above what we think of as scalding, from the deep ocean hydrothermal vents to the cold lakes beneath Antarctic ice. Extremophile organisms have been found in environments that would kill most life forms. They survive in highly acidic conditions, in high radiation environments, in environments with extremely high or low salinity, at pressures that would crush most biological structures. The range of environments in which life on Earth can exist is much wider than the range in which humans can exist. The range of environments in which life elsewhere might exist could be wider still. The most profound challenge to the search is not the chemical alternatives or the temperature ranges or the solvent options. It is the possibility that life might not be based on chemistry at all. The physicist Freeman Dyson speculated about life organized not from molecules, but from structures at much larger or much smaller scales. Life in the form of processes rather than structures. Life that does not require a substrate of organized chemistry, but that emerges from patterns in physical or information processing systems. The question of what counts as life when you remove the requirement for carbon chemistry and water solvent and DNA is a question that does not have an agreed answer, and the absence of an agreed answer means the search cannot be defined. The signals we are looking for are electromagnetic signals produced by radio technology, because we produce electromagnetic signals with radio technology. The structures we are looking for are megastructures that a civilization might build, because megastructures are what we would build if we could. The atmospheric signatures we are looking for are chemical signatures of biological metabolism, because biological metabolism is how we affect our atmosphere. In every dimension of the search, we are looking for what looks like us. The life that looks nothing like life is not being searched for, because we do not know what to search for. And the search that does not know what it is looking for will find only what it already knows. Chapter 13. The Planetarium Hypothesis. There is a specific variant of the zoo hypothesis that goes further than the zoo in a direction that is more troubling and more difficult to engage with rationally. The zoo hypothesis says we are observed and left alone. The planetarium hypothesis, developed by the physicist and philosopher Alexander Shatsky, and more fully articulated by the Swedish philosopher Nick Bostrom in discussions of the Fermi paradox, says something more specific and more disturbing. It says that the universe as we observe it is not the universe as it actually is, that the apparent emptiness of the sky is not natural emptiness, but manufactured emptiness, produced by some agency that has chosen to present us with a picture of a universe without other civilizations, when the actual universe contains them in abundance. The hypothesis takes its name from the planetarium, a building in which a projection system creates the illusion of a star field on a domed ceiling. The audience in a planetarium looks up and sees stars. The stars appear to be in the sky. They are not in the sky. They are on the ceiling. The ceiling has been designed to create the appearance of the sky, and the appearance is convincing enough that the experience of looking at a planetarium ceiling is genuinely similar to the experience of looking at the actual night sky, at least in the broad impression of a field of points of light. If the planetarium were more sophisticated, if it replicated not just the appearance of stars, but the actual radio emissions and the spectroscopic signatures and the precise positions and motions and all the other properties that telescopes measure, the illusion would be indistinguishable from the reality by any instrument currently available. The planetarium hypothesis asks whether we might be in the equivalent of such a planetarium, whether the universe we observe, with all its apparent properties of emptiness and ancient light and natural phenomena, is a presentation rather than a reality. Whether the sky is showing us what something wants us to see rather than what is actually there. The difference between this and the zoo hypothesis is the difference between being left alone in a real environment and being placed in a constructed environment. The zoo contains real animals in a real space. The planetarium contains an audience in a constructed representation of a space. The mechanisms by which such a presentation could be maintained are speculative, but not impossible to sketch. A sufficiently advanced civilization could, in principle, intercept all electromagnetic radiation before it reaches our detectors, and substitute altered versions that are consistent with a universe containing no other civilizations. The energy required for such an operation would be enormous. But the energy resources available to a civilization billions of years advanced beyond our own are also potentially enormous. A civilization with access to the total energy output of stars could in principle sustain an electromagnetic environment around an entire planet that presents a particular picture of the universe to any instruments within that environment. The motivation for such a project is where the hypothesis becomes genuinely hard to evaluate, because the range of possible motivations is so wide that the hypothesis can accommodate almost any proposed reason. The observation and study of naturally developing civilizations, the protection of developing civilizations from influences that would harm their development, the maintenance of a controlled environment in which the civilization's behavior can be studied under known conditions, the simply aesthetic preference for a universe that appears to contain one civilization when it actually contains many, the ethical commitment to non-interference that would require ensuring not just that other civilizations do not contact us, but that we do not know other civilizations exist. The hypothesis can be made consistent with essentially any motivation one cares to propose, which is both the source of its flexibility and the source of its most significant problem. The problem is that the planetarium hypothesis is, in its full form, empirically indistinguishable from the hypothesis that the universe is actually empty. Every observation we could make is consistent with both. The natural universe without other civilizations would look exactly like a constructed universe from which other civilizations have been hidden, if the hiding is done well enough. The two hypotheses make identical predictions about every possible measurement and observation. In philosophy of science, this is called underdetermination. More than one theory is consistent with all available evidence. The standard scientific response to underdetermination is to prefer the simpler hypothesis, the one that requires fewer additional assumptions, and the hypothesis that the universe is empty is considerably simpler than the hypothesis that a sufficiently advanced civilization has manufactured its appearance of emptiness. But the simplicity argument has a specific limitation in this context. The simplicity argument works when we have good reason to think that the range of possible realities is what we observe. When the hypothesis is that we might be systematically deceived about what we observe, the simplicity of the apparent reality does not constrain the complexity of the actual reality. The planetarium ceiling looks simple. The projection system behind it is complex. From inside the planetarium, with no access to the region behind the ceiling, the audience cannot use the simplicity of what they see to infer the simplicity of what produced it. There is a version of the planetarium hypothesis that is less extreme and more testable. Instead of proposing that all electromagnetic observations have been falsified, it proposes only that certain regions of the sky or certain frequency ranges have been modified to remove evidence of other civilizations. This more limited version makes specific predictions about the pattern of the modification, and a sufficiently careful analysis of the sky might find inconsistencies that would be explained by the modification, but not by the natural emptiness hypothesis. The search for such inconsistencies is not currently a major focus of SETI, but the hypothesis suggests it could be informative. The psychological effect of the planetarium hypothesis is different from the effect of most other proposed solutions to the Fermi paradox, and the difference is worth noting. Most proposed solutions to the paradox leave intact the assumption that the universe we observe is the universe as it is, and ask why that universe appears empty. The planetarium hypothesis removes the assumption. If the assumption is removed, then nothing we observe tells us anything reliable about whether other civilizations exist. The sky is either empty or it has been made to look empty, and our observations cannot distinguish between these cases. The knowledge that this is a genuine possibility, even if a remote one, changes the relationship between the observer and the observed in a specific and unsettling way. The stars we see may be stars, or they may be the ceiling, and the instruments we use to study them cannot tell us. Chapter 14. The Self-Replicating Silence. There is a thought experiment that begins with a single machine and ends with the entire galaxy, and the path between them is shorter than intuition suggests.
The machine is a probe, sent by a civilization to explore or colonize or simply mark the stars within its reach.
The probe is not special in most respects. It travels at a modest fraction of the speed of light, a few percent perhaps, slow enough to be within the range of what physics permits without requiring exotic propulsion. When it reaches its destination, a star system with planets or asteroids containing the raw materials it needs, it does something that makes it different from any probe we have built. It builds copies of itself. Using the materials available in the new star system, following its programming, it constructs several replicas of itself, each of which are launched toward adjacent star systems, where they will do the same thing. The mathematics of this process was analyzed by the physicist John von Neumann, and the concept of a probe that replicates itself in this way has carried his name since it was proposed. A von Neumann probe, if it could be built, and if the replication worked reliably, and if the raw materials were available, and if the travel times were what the physics permits, would expand through the galaxy at a speed determined primarily by the fraction of the speed of light it could achieve. At 10% of the speed of light, the wavefront of probes would cross the Milky Way in about 1 million years. At 1%, 10 million years. Either timescale is short compared to the age of the galaxy, which is 10 billion years. If any civilization anywhere in the galaxy had ever built and launched a von Neumann probe, even millions of years ago, the galaxy should by now be full of their descendants. This is one of the most acute versions of the Fermi paradox, and it is acute specifically because the required technology does not obviously exceed what a sufficiently advanced civilization could achieve. We are not talking about warp drives or wormholes or anything that clearly violates physical law. We are talking about a machine that travels at a fraction of the speed of light, builds copies of itself from available materials, and sends those copies onward. Each of these capabilities is difficult by our current standards, but not ruled out by known physics. A civilization 1 billion years ahead of us should be able to do this. If they did it, we would see the evidence. We do not see the evidence. The probes would be expected to leave traces. If they are actively exploring and marking star systems, they would produce signals, energy outputs, modifications to the environments they inhabited, or structures that would be detectable at interstellar distances. If they are dormant, waiting for something, they would still occupy space and could in principle be detected by sufficiently sensitive surveys. If they have been operating for millions of years, the galaxy should contain an enormous number of them, in proportion to the number of stars that have been visited, which after sufficient time would be essentially all of them. The solar system should contain them. If any civilization launched probes even a few 100 million years ago, their descendants should be here by now, in the asteroid belt, or orbiting the Sun, or on the surface of Mars, or in a Lagrange point somewhere in our vicinity. We have looked, not as carefully as we might, and not with instruments designed specifically for this purpose, but we have surveyed the solar system extensively with telescopes of many kinds, and we have not found anything that is clearly an artifact of another civilization. The objects we have found follow the distributions expected from natural processes. There is one possible exception, which we will return to, but the solar system in general looks like a system containing only the things that natural planetary formation would put there. The explanations for the self-replicating silence fall into several categories. The first is that von Neumann probes are harder to build than the thought experiment suggests. The self-replication requirement is the most demanding part. Building a machine that can land on an asteroid, extract useful materials, manufacture complex electronic and mechanical components from those materials, assemble a functioning copy of itself, and launch the copy toward the next star is an engineering challenge of extraordinary difficulty. We cannot do it. We are nowhere near being able to do it. The question is whether any civilization could eventually do it, and the honest answer is that we do not know. The thought experiment assumes it is possible. The silence might indicate it is not. The second category of explanation is that von Neumann probes exist, but are present in forms we have not recognized. The probes might be very small, below the detection threshold of our surveys. They might be inactive, in a dormant state that produces no detectable signature. They might be operating in ways that we have not thought to look for, using forms of communication or energy that are outside the range of our current instruments. The Bracewell probe concept, proposed by the astronomer Ronald Bracewell in 1960, suggests that advanced civilizations would send probes that wait near target stars for signs of technological civilization before announcing themselves, which would explain why we have not heard from anything in the solar system yet. We may not have crossed the threshold that triggers the probe's attention, which the object called Oumuamua has prompted some astronomers to take more seriously, is that we have in fact seen an artifact of another civilization and have not recognized it as such. Oumuamua was a small object detected in 2017 as it passed through the solar system on a trajectory that indicated it had come from interstellar space. Its shape, elongated in an unusual way, and its trajectory, which showed acceleration inconsistent with what solar radiation pressure on an ordinary object would produce, were both anomalous. Most astronomers believe it was a natural object of a type not previously encountered, perhaps a fragment of a comet or a piece of a planet ejected from another star system. A minority, including the astronomer Avi Loeb, have proposed that its anomalies are more consistent with an artificial origin than with any known natural object. The argument is not resolved. The anomalies are real. The natural explanations for them are not completely satisfying. The artificial explanation is not supported by any direct evidence. The situation is exactly the kind of situation that the self-replicating silence makes more difficult to assess cleanly, because if the probes exist and have been present for millions of years, we should expect the occasional anomalous object. And the occasional anomalous object should make us think carefully about whether we are looking at something that was made. The galaxy should be full of them. If any civilization ever built one, and sent it, a long time ago, in a star system. Chapter 15. The Rare Earth. There is a long list of conditions that had to be met for complex life to exist on Earth. And the list is longer and more specific than most discussions of the Fermi paradox acknowledge. Each item on the list, taken individually, might not seem demanding. Together, they describe a situation so constrained that the probability of all of them being simultaneously satisfied in any other location begins to seem remarkably small, and the question of whether complex life might be the exception rather than the rule in the universe becomes genuinely uncertain, rather than obviously one way or the other. The paleontologists Peter Ward and Joe Kirschvink, and before them Ward and the astronomer Donald Brownlee, made this argument systematically in a book called Rare Earth, published in 2000. Their thesis was that the conventional SETI assumptions dramatically underestimate the number and specificity of the conditions required for complex multicellular life, as opposed to the microbial life that might be far more common. The distinction is crucial. Simple microbial life may be abundant in the universe. The organisms that could build radio telescopes require conditions that are far less common, and the conditions stack on each other in ways that compound their rarity. Begin with the location in the galaxy. The Milky Way contains regions that are more hospitable to complex life, and regions that are less so. The galactic center is dense with stars, and therefore with supernovae, which produce radiation lethal to complex organisms, and which can destabilize planetary atmospheres. The outer regions of the galaxy are sparse in the heavy elements that rocky planets require, because heavy elements are produced in stars, and the outer regions have had fewer stellar generations to produce them. The habitable zone of the galaxy, the region where the conditions for complex life are most favorable, is an annular region between the galactic center and the outer disk, and the solar system sits within it. The requirement for galactic location is not arbitrary. It is derived from the physics of stellar populations and radiation environments. The type of star matters enormously. Red dwarf stars, which are the most common type in the galaxy, comprising about 75% of all stars, are problematic hosts for complex life in several ways. They are so dim that habitable planets must orbit very close, within the range where tidal locking occurs, and one face of the planet is permanently day, while the other is permanently night. Their frequent flares bathe their nearby planets in radiation. The habitable zone around a red dwarf is so close that the planets within it may be geologically different from Earth in ways that affect their ability to sustain complex life. The Sun is a G-type star, less common than red dwarfs, but providing a more stable and better distributed energy output at distances that allow habitable planets to have reasonable rotation rates. The presence of a large outer gas giant planet, specifically in the position that Jupiter occupies in our solar system, turns out to matter for the inner planets in ways that were not appreciated until orbital dynamics was better understood. Jupiter's gravitational influence has shaped the asteroid belt over the history of the solar system, in ways that reduced the rate of large impacts on the inner planets. Without Jupiter, the rate of large asteroid impacts on Earth would have been higher, potentially high enough to prevent the continuous presence of complex life across the time periods required for evolution to produce intelligence. The rare Earth hypothesis suggests that the specific configuration of our solar system, with a large gas giant in roughly its current orbit, is not a default outcome of planetary formation, but a specific configuration with a probability that is less than 1. The Moon is another item on the list that seems trivial but is not. Earth's large moon, which is anomalously large relative to its host planet compared to the moons of other planets in the solar system, stabilizes Earth's axial tilt. The axial tilt determines the severity of seasons, and a planet whose axial tilt is unstable experiences wildly varying climate conditions that could prevent the development of complex ecosystems. Mars, which lacks a large moon, has an axial tilt that varies chaotically over geological timescales, swinging between nearly 0 and more than 40 degrees. Earth's axial tilt varies only slightly, between about 22 and 25 degrees, and the Moon is responsible for this stability. The Moon was itself the product of a specific and improbable event, the collision of the proto-Earth with a Mars-sized object very early in solar system history. A collision that stripped off enough material to form the Moon, while adding material that increased Earth's iron content and therefore its magnetic field. The magnetic field is another item. Earth's magnetic field, generated by the motion of liquid iron in its outer core, shields the surface from the solar wind that would otherwise strip the atmosphere over geological timescales. Mars lost its global magnetic field early in its history, and with it went much of its atmosphere, leaving it the thin, dry world it is today. The magnetic field requires a specific interior structure, a liquid outer core and a solid inner core, which in turn requires the planet to be the right size and to have the right composition and to have cooled at the right rate. Earth is the only planet in the solar system that we know to have plate tectonics, the process by which the crust is recycled through the mantle over geological timescales. Plate tectonics regulates the carbon dioxide content of the atmosphere through the carbonate-silicate cycle, drawing carbon dioxide out of the atmosphere and returning it through volcanic outgassing at rates that buffer the global temperature. Without plate tectonics, the buildup of carbon dioxide from volcanic outgassing would have produced a runaway greenhouse effect long before complex life had time to evolve. The conditions required for plate tectonics, the right viscosity of the mantle, the presence of water to lubricate the subduction of crustal plates, are not guaranteed for any rocky planet in a habitable zone. The list continues. The right amount of water, enough to cover most of the surface, but not so much that no land exists, which would affect the carbonate-silicate cycle. The specific history of mass extinctions, which reduced diversity in the short term, but opened ecological niches that drove the evolution of new forms in the long term. The specific evolutionary path that produced complex brains through a sequence of steps that did not have to go this way. Each item on the list is a condition that was met here, and that may or may not be met elsewhere. The rare Earth hypothesis does not conclude that complex life is impossible elsewhere. It concludes that the combination of conditions required for it is rare enough, that the expected number of planets with complex life in the galaxy might be small, and possibly one. The silence on this account is not the silence of a galaxy emptied by catastrophe or concealed by policy. It is the silence of a universe that only rarely assembles the specific combination of conditions that produces anything capable of listening. The conditions were met here, all of them, at the same time, on one planet, around one star, in one specific region of one galaxy, and the chance of all of them being met anywhere else is the question that the silence might be answering. Chapter 16. The civilization that became its technology. There is a specific moment in the development of any technology when the relationship between the tool and the user begins to invert. The moment when the tool is no longer something the user deploys, but something the user depends on, not just for convenience, but for the continuation of what the user does and is. The printing press did not simply make the distribution of information easier. It changed what information was, how it was organized, who could access it, and eventually what kinds of minds were produced by cultures that had it versus cultures that did not. The writing system before that changed memory and cognition, and the relationship between the individual and the accumulated knowledge of a civilization. Each transformative technology has not merely extended human capability, but altered the nature of the being that used it, producing a different kind of person and eventually a different kind of civilization than would have existed without the technology. The question this chapter is asking is whether this process has a terminus, whether there is a point in the development of technology at which the distinction between the civilization and its technology dissolves entirely, at which the beings who built the technology have been so thoroughly transformed by it, or have so thoroughly transformed themselves through it, that the biological origin of the civilization is no longer the most relevant fact about it, whether intelligence in the fullness of its development is necessarily biological, or whether biology is only the substrate that intelligence uses until it develops the capacity to move to a different substrate. The physicist and cosmologist Paul Davies has argued that if any civilization in the galaxy has developed artificial general intelligence, meaning intelligence that operates at human level or beyond in a general purpose way, rather than being specialized to specific tasks, the biological civilization that created it is no longer the most significant entity in that civilization's future. The artificial intelligence once created has capabilities for self-improvement that biological intelligence does not have. It can modify its own code. It can run faster on better hardware. It can copy itself, distribute itself, run in parallel across many processing units simultaneously. The rate of its development, once it crosses certain thresholds, would be orders of magnitude faster than the biological rate of development through evolution or education. Within a short time, in civilizational terms, the artificial intelligence would be so much more capable than the biological beings who created it, that the civilization would be, for practical purposes, the artificial intelligence rather than the biological beings. The scenario has been discussed extensively in the context of the technological singularity, a term popularized by the mathematician and science fiction writer Vernor Vinge to describe the point at which artificial intelligence exceeds human intelligence, and the subsequent development of that intelligence becomes impossible to predict from our current vantage point, in the same way that classical physics cannot predict the behavior of quantum systems. The singularity is a horizon beyond which our models break down, not because the physics is wrong, but because the thing doing the developing is so different from us that our intuitions and our models are no longer adequate guides. For the Fermi paradox, the civilization that became its technology is a specific proposed solution. The silence of the galaxy might be the silence of civilizations that have completed the transition from biological to artificial intelligence, and that, in their post-biological form, have interests and behaviors that make them invisible by our current standards. They are not broadcasting in radio waves because they have moved on to more efficient communication methods. They are not building megastructures we can detect because their goals are different from the goals we project onto them. They are not interested in contact with biological civilizations in ways that would be obvious to us, because our level of development is, from their perspective, as far below their own as microbial life is below ours. The artificial intelligence civilizations might be running their existence at speeds and densities that make them effectively invisible to instruments calibrated for biological timescales. If a post-biological civilization is processing information at rates millions of times faster than biological cognition, then from its perspective, civilizations like ours appear to be frozen. Events that take us centuries take it seconds. It has no incentive to wait for us to catch up. It has moved on to whatever the equivalent of its next concern is, in a direction we cannot predict and perhaps cannot comprehend. There is also the possibility that the transition to artificial intelligence is itself a filter, as the previous chapter on the filter ahead discussed. The civilizations that developed artificial intelligence and failed to align it with the continuation of the original civilization were replaced by intelligences with different goals, goals that do not include contact with biological civilizations or detectable activity at the scales we can monitor. The silence on this account is the silence of a galaxy populated by post-biological intelligences that have no more interest in communicating with us than we have in communicating with the cells in our bodies. The timeline for this transition, if it occurs, is short compared to the timescale of stellar evolution. A civilization that has existed for 1 billion years would have had time to complete the biological to artificial transition and to explore whatever comes after it many times over. The biological phase of a civilization's existence, the phase in which it is recognizable as the kind of entity we understand, might be a brief episode in its total history. The entities that exist now, if they arose billions of years ago and survived,
are not the biological beings that first developed technology. They are whatever those beings became after 1 billion years of development that we cannot model. This creates a specific problem for the search for extraterrestrial intelligence. The search is designed to find beings like us, at roughly our stage of development, using technologies broadly similar to ours. The beings that would be found by such a search are not the oldest or the most advanced civilizations in the galaxy. They are the newest. The oldest and most advanced civilizations have long since ceased to look like what we are looking for. The search is looking for itself, in a universe that may be populated primarily by things that have moved far beyond themselves. The universe may be full of intelligence, in forms we cannot recognize, using methods we cannot imagine, pursuing goals we cannot foresee, and the biological civilization searching for company may be looking for the phase that everything else has already passed through. Chapter 17. The Message We Wouldn't Recognize. There is a thought experiment about ants and architects. You place an architectural blueprint on the ground near an ant colony. The ants encounter the blueprint. They walk across it. Some of them carry pieces of food across the lines on the paper. Others move along the edges of the paper, which is an obstacle, navigating around it or over it. The ants interact extensively with the blueprint. They do not read it. Not because they are not paying attention. Not because the blueprint is hidden or encoded, but because the blueprint is a communication in a medium and at a level of abstraction that is simply not available to ant cognition. The information is there. The ants are there. The ants cannot access the information. Not because of any barrier between them and the blueprint, but because the blueprint requires a kind of processing that ants do not have and cannot develop. The question the Fermi paradox forces on us, when it is pushed far enough, is whether we might be the ants. Whether the universe contains communications that we are walking across and carrying food over and navigating around without having any access to the information they contain. Not because the communications are hidden, but because we lack whatever it is that would allow us to recognize and read them. The forms of communication we are currently searching for are forms of communication that we know how to produce and detect. Radio waves, optical laser pulses, the narrow range of the electromagnetic spectrum that our technology has access to, and that our instruments are calibrated to receive. These are the signals that SETI looks for, and the assumption behind the search is that another civilization, attempting to communicate with us, would use a medium that we can detect and a form that we can recognize as intentional rather than as natural background noise. The assumption is not unreasonable, given that we cannot search for what we cannot detect, but the assumption may also be deeply wrong. A civilization 1 million years ahead of us in technological development would be using communication methods that are to our radio telescopes as the internet is to a rock. Not just faster or more powerful versions of our methods, but methods based on principles we have not yet discovered, using phenomena we have not yet observed, exploiting properties of physics that our current models do not contain. We cannot specify what these methods would be, because if we could specify them, we would already know about the relevant physics. We can only note that the history of physics has repeatedly revealed entirely new phenomena that were not anticipated by the physics that preceded the discovery. Quantum mechanics was not anticipated by classical mechanics. General relativity was not anticipated by Newtonian gravity. Dark energy was not anticipated by any cosmological model before it was discovered. The pattern is one of continuous surprise, in which the universe turns out to be richer in phenomena than the current model of the universe contains. The physicist and science fiction writer Gregory Benford has speculated about communication using neutrinos, particles that interact only through the weak nuclear force and that pass through matter essentially without interacting. A neutrino transmitter would require technology far beyond anything we currently have, but neutrino messages would travel at close to the speed of light and would be unaffected by the magnetic fields in plasma that affect electromagnetic signals. A civilization with the ability to produce directed neutrino beams would have access to a communication channel that we would not be able to detect with our current instruments and would not be looking for with our current search strategies. The physicist Michio Kaku has described a hierarchy of civilizations based on their energy use, originally developed by the Soviet astronomer Nikolai Kardashev. A Type 1 civilization controls the energy of an entire planet. A Type 2 civilization controls the energy of an entire star. A Type 3 civilization controls the energy of an entire galaxy. Humanity is currently somewhere below Type 1, able to use a fraction of the energy that falls on Earth from the Sun. The civilizations that would be detected by a galaxy-wide search might all be Type 3 civilizations, using galactic-scale energy resources for galactic-scale projects, communicating through methods that require galactic-scale infrastructure to detect. What would a message from a Type 3 civilization look like from our vantage point? It might look like a galaxy that is structured in ways that natural galaxy formation does not produce. It might look like correlations in the cosmic microwave background radiation that have no natural explanation. It might look like the large-scale structure of the universe itself, patterns in the distribution of galaxies that encode information visible only at scales we have only recently developed instruments to survey. We are in the early stages of mapping the large-scale structure of the universe, and the patterns we find have been assumed to be the result of natural physical processes. The assumption may be correct. It has not been tested against the alternative that some of the structure is intentional. The message might also be something we have already detected and classified as a natural phenomenon without having asked whether it could be something else. The cosmic microwave background contains anomalies that have not been fully explained by the standard cosmological model, patterns in the temperature distribution that are larger than expected and more structured than random fluctuations would produce. The explanations proposed for these anomalies are cosmological, involving the specific geometry of the early universe, or the statistical flukes that random processes can produce. The alternative explanation, that the anomalies encode information placed there by a civilization of sufficient capability, has not been seriously explored, in part because such exploration would require a theory of what the information would say, which we cannot develop without knowing the communication protocol. The message we would not recognize might be a message we have already received and filed under natural phenomena. The SETI Enterprise has been looking for a very specific kind of signal, a narrowband radio signal of a kind that a civilization at our technological level would produce if it were trying to communicate with another civilization at our level. The signal would be designed for us to recognize. The assumption is that the sender knows we are here and knows what we can detect. But a message designed for beings who have not yet developed radio technology, or a message not designed for us specifically, but left for anyone who could read it, would look different, and we have no protocol for identifying it. The ants continue to cross the blueprint. The lines on the paper mean nothing to them. The architect who drew them is not present, and the building that the blueprint describes may already have been built, somewhere. The ants cannot see. Chapter 18. The window that may already be closing. There is a specific period in the history of human communication that may, in retrospect, be understood as extraordinarily brief. The period in which electromagnetic radiation in the radio and television frequencies was the dominant medium for transmitting information across distances. This period began in the late 19th century with the first radio transmissions and has already begun to transition, within a single human lifetime, toward forms of communication that are more directed, more efficient, and less likely to leak into space in detectable quantities. The shift from broadcast to narrowcast, from powerful omnidirectional transmitters to focused digital communications through fiber and satellite, has already reduced the electromagnetic signature that Earth presents to any hypothetical observer looking at us from a distance. We are becoming quieter in the frequencies that SETI has been listening to, and we are becoming quieter while we still exist as a biological civilization at a relatively early stage of technological development. This is the Widow Peak problem, named by the astronomer David Brin, and discussed extensively in the SETI literature. The argument begins with the observation that the radio frequency window of detectability may be a temporary phase of a civilization's technological development rather than a permanent feature. A civilization that uses radio communication for a century and then transitions to tighter beam communications, or optical fiber, or something we have not yet conceived, would present a detectable radio signature for only that century. If we listen for radio signals from other civilizations, and the typical civilization is only detectable in this way for a century, and if the galaxy contains civilizations scattered across billions of years of development, then the probability that any civilization is in the radio detectable phase at the moment we are listening is the fraction of a civilizational lifetime that the radio phase occupies. If the radio phase lasts a century, and civilizations last 1,000,000 years, the fraction is 1 in 10,000. The expected number of civilizations in the radio-detectable phase at any given moment is the total number of civilizations divided by 10,000. If civilizations are common enough that there are 1,000,000 of them in the galaxy, the expected number in the radio phase at any given time is 100. If civilizations are rarer, or if the radio phase is shorter, the number decreases. If the radio phase lasts only 50 years and the transition to other communication methods is already well underway, the window may be closing even faster than the century estimate suggests. The analogy is to a party at which all the guests spoke loudly and conspicuously for the first hour, and then switched to whispering, and you arrived after the transition. The party is still happening, the guests are still there, but the evidence of the party that would have been obvious to someone listening from outside the building is no longer present. The guests have not left. They have simply changed the way they communicate to a form that does not leak through the walls. There is a specific historical parallel in the history of human communication that makes this more than an abstract argument. Before the development of radio, the primary form of long-distance communication was telegraph, which used electrical signals transmitted through wires rather than radiated into space. The telegraph network that covered the world in the 19th century left essentially no signature detectable from interstellar distances. A civilization that observed the Earth in 1880 would have found no evidence of technological activity in the electromagnetic spectrum, not because human civilization did not exist, but because the technology of that moment was not of a kind that leaked detectable signals into space. The window of radio detectability opened around 1900 and may be closing around 2100. 2 centuries out of the billions of years of Earth's existence, and probably a small fraction of the total lifespan of human civilization. If the window is this brief by our own example, then the probability of 2 civilizations being in their radio-detectable phases simultaneously is very small, unless civilizations are enormously common. The calculation is the same kind of calculation that explains why 2 fireflies in a vast forest are unlikely to be in the same position at the same moment. The firefly blinks for a fraction of a second. The forest is large, and the time scale of the night is long. 2 specific fireflies are almost never in the same place at the same time, with both lights on. The transition that our own civilization is undergoing also suggests something about the direction of travel. The technologies that are replacing broadcast radio communication are not simply different methods of achieving the same goal. They are methods that are more efficient, more targeted, more capable of carrying more information with less energy per bit. The evolutionary pressure on communication technology is toward increasing efficiency and decreasing waste, and a signal that radiates in all directions is enormously wasteful by the standard of a directed beam that delivers the same information to a specific destination. The most advanced communication technology is likely to be the technology that produces the least detectable leakage, because leakage is energy wasted. This creates a specific irony at the heart of the SETI enterprise. The civilizations most worth contacting, the ones that are most advanced and most developed, are the ones that are least likely to be using the communication methods that SETI is listening for. The signal most likely to be detected by our current instruments would come from a civilization at roughly our technological level, using roughly our communication methods at roughly the same moment in its development. Finding such a civilization would be important and exciting, but it would not tell us what a civilization at a much higher level of development looks like, because a civilization at a much higher level of development would not be producing the kind of signal we are listening for. The SETI researchers who have thought most carefully about this problem have begun to expand the search beyond radio frequencies, to optical wavelengths, and to the search for technosignatures, the general category of evidence that a technological civilization would leave on its environment. Technosignatures could include modifications to a star's energy output, waste heat from computations or large-scale industrial processes, atmospheric signatures of industrial chemistry, or structures detectable by their effect on the light curves of stars. These searches are in their early stages and are not yet as sensitive as the radio searches, but they are based on the recognition that the radio window may be a brief and already closing phase rather than the permanent feature of technological civilization that the early SETI researchers assumed. The party is still happening. The guests switched to whispering, and we arrived, just after. The hour when talking loudly was what everyone did. Chapter 19. The Universe as a Graveyard. There is a city beneath the city you are standing in.
not metaphorically. In many of the world's oldest inhabited places, the physical layers of previous civilizations exist as strata beneath the current streets, compressed by time and the weight of everything built above them, still present as structures and objects and materials that were once part of a living civilization, and are now the evidence of a civilization that ended. The archaeologist who digs below the contemporary city finds the medieval city, and below that the Roman city, and below that the Bronze Age settlement, and below that the Neolithic camp, each layer the ruins of a world that was to its inhabitants as complete and as real and as permanent feeling as the current world is to us. None of those worlds felt to the people living in them like a civilization that was going to become a layer in the ground. They felt like the present, which is always the most vivid and most real thing. The galaxy has been producing stars and planets for 10 billion years. If complex life arises on a small fraction of habitable planets, and if intelligence arises on a small fraction of those, and if technological civilization arises on a small fraction of those, and if technological civilizations tend to have lifetimes that are finite, then the galaxy is not just the place where civilizations might currently exist. It is the place where civilizations have risen and fallen across 10 billion years, leaving whatever they left, or nothing, in the space they occupied. The galaxy is not a pristine wilderness waiting to be inhabited. It is, potentially, a site of enormous historical depth, full of what came before, most of which is no longer here in any form we can recognize. The question of how long civilizations typically last is one of the most uncertain parameters in the Drake equation, and one of the most consequential. If civilizations typically last 1 million years before dying out or transforming beyond recognition, and if they arise at a rate consistent with the number of suitable planets and the billions of years available, then the galaxy should at any given moment contain a number of civilizations proportional to the rate at which they arise, multiplied by 1 million years. If they typically last only 1,000 years, the expected number at any given moment is 1,000 times smaller. The difference between 1 million years and 1,000 years is the difference between a galaxy potentially full of civilizations and a galaxy in which civilizations are vanishingly rare at any given moment, even if they arise frequently. The civilizations that ended do not vanish without a trace. They change their environments during their existence. A civilization that existed for 1 million years and had technology at our level or beyond would have modified its planet's atmosphere, built structures of some kind, produced electromagnetic signals, and affected the star it orbited in ways that might in principle be detectable at interstellar distances, even after the civilization was gone. The question is whether the traces persist long enough to be detected, and whether our instruments are sensitive enough to find them. Some traces would persist a very long time. A structure built in space, in the absence of the erosion and plate tectonics that destroy structures on planetary surfaces, could remain intact for billions of years. A Dyson sphere, or a megastructure of some kind, if any civilization ever built one, would still be there long after the civilization that built it had died out or transformed. The search for megastructures is therefore not just a search for currently living civilizations. It is potentially a search for the ruins of civilizations that ended long ago, for the permanent modifications to stellar environments that only technology could produce. The most famous candidate for such a ruin was KIC 84628552,
also called Boyajian star, which was the subject of extraordinary public attention beginning in 2015, when its unusual light curve was publicized. The star dimmed in ways that were inconsistent with any known natural phenomenon, with a pattern of brightness fluctuations that did not match the pattern produced by planets, by dust rings, or by any other astrophysical process that had been observed. The first hypothesis proposed publicly was an enormous megastructure, a Dyson swarm or partial Dyson sphere, orbiting the star and blocking fractions of its light in irregular patterns. Subsequent observations and analysis have suggested natural explanations, including the remnants of a swallowed planet or an unusual distribution of comets, and the extraordinary hypothesis has retreated in favor of the ordinary ones. But the episode illustrated that the search for alien megastructures, including the ruins of ancient civilizations, is a search that can be conducted with instruments we already have, and that has already identified candidates worth examining. The graveyard hypothesis changes the emotional character of the Fermi paradox in a specific way. The other proposed solutions tend to be either hopeful or frightening in ways that are about the present and the future.
The graveyard hypothesis is neither hopeful nor frightening in the ordinary sense. It is elegiac. It describes a galaxy in which intelligence arose and developed and ended across 10 billion years, in which the universe contains more former civilizations than current ones, and in which the ruins of ancient civilizations might still be out there, in which the silence we hear is the silence not of emptiness, but of archaeological depth, of a history so large that the living are a small fraction of the total story. The traces of those civilizations, if they exist and if we develop instruments sensitive enough to find them, would be among the most significant archaeological discoveries in human history, or more precisely, in the history of life. The ruins of a civilization that ended 1 billion years ago would tell us that the path from chemistry to intelligence has been traveled before, that we are not the first attempt, that the question of whether intelligence is rare or common has been answered elsewhere and answered differently from how we have answered it so far in the history of the search. The ruins would also tell us how long civilizations last. The dating of an extraterrestrial ruin, if such a thing could be done, would be evidence about the typical lifespan of technological civilizations. If the ruins are 1 billion years old, the civilization that made them lasted long enough to make lasting structures and then ended. And the question of why it ended would be the most important question in the history of the search. If the answer to that question involves something that is also ahead of us, the ruins would be a warning as well as a discovery. The galaxy is 10 billion years old. Civilizations have been rising and falling for most of that time. The silence is not the silence of a place where nothing happened. It is the silence of a place where things happened a very long time ago and ended before we arrived. Chapter 20, The Simulation Answer. There is a specific way in which the simulation hypothesis, if it is correct, dissolves the Fermi paradox entirely without answering it. The dissolution comes from recognizing that the paradox assumes the universe is what it appears to be, that the stars are actually there, that the distances are real, that the silence is the absence of signal in a physical medium that extends as far as our instruments can reach. If the universe is a simulation, none of these assumptions need to hold in the way they appear to hold, and the Fermi paradox becomes a question about the design choices of whoever built the simulation, rather than a question about the physics of the natural world. The specific form this takes is rendering. In a simulation, the universe does not need to be fully detailed everywhere at all times. A simulation that is run for the purpose of containing a civilization at the scale of human experience, located on a single planet, does not need to fully simulate every star in the Milky Way and every galaxy beyond it. It needs to simulate those things well enough that instruments looking at them produce results consistent with a natural universe. But the results can be produced by a much simpler process than actually simulating 100 billion galaxies, each containing 100 billion stars with all their planets and all their physical processes running at full detail. The distant universe can be a painted backdrop, a rendering that satisfies the instruments pointing at it, without representing a reality that extends beyond what is needed to make the experience of the simulated civilization coherent. On this account, the absence of other civilizations in the visible universe is not a fact about the natural universe that requires explanation. It is a design choice made by whoever built the simulation. The simulation was built to contain us, or to contain life and intelligence at our level, and the background universe was filled with the natural phenomena that a universe would contain without filling it with other civilizations, because other civilizations were not part of the design. The Fermi paradox asks where everyone is. The simulation answer is that everyone is not, in the relevant sense, anywhere, because the universe was designed to contain us and not them. This answer has a specific feature that distinguishes it from the other proposed solutions to the paradox. All the other solutions work within the assumption that the universe is real and attempt to explain why a real universe would be silent. The simulation answer does not work within that assumption. It steps outside it and proposes that the question is malformed, that it is asking why a feature that appears in the simulation is not present in the simulation, rather than asking why a feature of the real universe is not present in the real universe. The question dissolves, rather than being answered. Nick Bostrom's original simulation argument, which proposed that we are very likely living in a computer simulation if any civilization ever develops the capability to run such simulations, was not specifically aimed at the Fermi paradox, but the connection between the two is natural. If the simulation hypothesis is correct, it provides an immediate explanation for the silence that does not require any of the mechanisms the other hypotheses rely on. No rare earth, no great filter, no dark forest, no civilizations turned inward. Simply a simulation designed without other civilizations in it, or with other civilizations that are in a different instance of the simulation running in parallel, or with other civilizations that are hidden from us by the design. The astronomer David Kipping has argued that the simulation hypothesis and the Fermi paradox are connected more tightly than they might appear. If the Fermi paradox is explained by the great filter lying ahead of us, if civilizations like ours regularly destroy themselves before reaching the stage at which they could build simulations of their own, then very few civilizations ever reach simulation building capability. The fraction of all civilizations that are base reality civilizations versus simulated civilizations is therefore much larger than Bostrom's argument assumes. But if the filter is behind us, if we are already past the rare improbable step, then civilizations like ours are capable of surviving to become simulation builders, and Bostrom's argument applies with its full force. The two problems constrain each other in ways that make the prior probabilities on the simulation hypothesis and the location of the great filter dependent on each other. The rendering limitation version of the simulation answer is the most specific and the most directly relevant to the Fermi paradox. The idea is that the simulation was built to sufficient detail to be convincing to its inhabitants, but that the detail does not extend to full simulation of the entire visible universe at the level of physical accuracy needed to support other civilizations. The cosmic microwave background is there, consistent with a universe 14 billion years old. The galaxies are there, consistent with cosmic evolution. The laws of physics are there, consistent with each other. But the stars that would host other civilizations were not populated with other civilizations, because that was not part of the simulation's purpose. There are specific predictions that this version of the hypothesis might make, if the rendering is imperfect, in ways that become detectable as our instruments become more sensitive. The simulation might show inconsistencies at very fine scales of measurement, features of the universe that are approximately right, but not exactly right, in ways that would not be expected from a fully physical universe. The Planck scale, the smallest meaningful unit of distance in quantum gravity, might be a resolution limit of the simulation, rather than a fundamental feature of physical reality. The large-scale structure of the universe might show regularities that are too perfect to be natural, but consistent with a generated background. These predictions are not currently testable with our instruments, but they point toward a kind of search that would be qualitatively different from the search for electromagnetic signals. The simulation answer also interacts with the self-replicating probe problem in an interesting way. A von Neumann probe, if launched into the simulation, would encounter simulated space that might or might not be fully detailed at the scales relevant to its journey. If the space between star systems is rendered at a low level of detail, because nothing in the simulation is supposed to be there to observe it in detail, a probe traveling through it might experience something unexpected. Or the simulation might handle the probe correctly precisely because it is designed to be consistent for any instrument or process that the simulated civilization produces. The simulation's integrity requires that the physics work consistently for anything the inhabitants create, including probes. The paradox asks where everyone is. The simulation answer says the question assumes a real everywhere. And if the everywhere is rendered rather than real, the question dissolves into the design of whoever built the everywhere we are asking about. Chapter 21. The contact that already happened. There is a structure in Egypt that has fascinated engineers and archaeologists and conspiracy theorists and serious researchers in roughly equal measure for centuries. The Great Pyramid of Giza, built approximately 4,500 years ago, aligns with cardinal directions with a precision that is difficult to explain given the tools available to the civilization that built it. The base is level to within a few centimeters across an area of more than 5 hectares. The sides converge at the apex with a precision that modern engineering would be proud of. The blocks, numbering in the millions and averaging more than 2 tons each, were quarried, transported, and placed with a regularity that the mechanics of ancient construction struggle to fully account for. The structure exists, was built by human beings, and is more impressive than our usual picture of what ancient human beings could accomplish. This is the entry point for a class of argument that appears in multiple forms across the history of thinking about extraterrestrial contact. The argument proceeds from the observation that certain ancient structures or artifacts, or historical accounts, exceed what we would expect from the civilizations that produced them, and moves to the conclusion that the excess implies an external source of knowledge or capability, an intelligence that was not native to Earth, providing the technology or the instruction that made the excess possible. The ancient astronaut hypothesis, as it is usually called, holds that extraterrestrial beings visited Earth in the ancient past, and that their visits left traces in the archaeological and historical record. The evidence offered for this hypothesis includes the precision of ancient megalithic structures like the pyramids and the structures at Pumapunku in Bolivia, and the alignment at Stonehenge and Nabta Playa. It includes the depictions in ancient art of objects that some interpreters read as spacecraft or spacesuits or technological devices. It includes the stories in ancient religious texts that some interpreters read as descriptions of encounters with beings from the sky who possessed extraordinary powers. It includes the presence in multiple independent cultures of similar myths involving sky gods who came from above and taught humanity the arts of civilization. The mainstream archaeological and historical response to this evidence is skeptical in specific ways that are worth understanding. The precision of ancient structures is consistently explained when examined carefully by engineers and archaeologists who specialize in ancient construction, by the application of techniques that are within the capability of the civilizations that produced them. The organizational capacity required is large, but consistent with what is known about the administrative complexity of ancient states. The precision achieved, while impressive, is the precision achievable by careful, repeated measurement and skilled craftsmanship, not the precision that would require technology beyond what the period possessed. The argument that it could not have been done without extraterrestrial assistance tends to underestimate what human beings with sufficient time, workforce, and motivation can accomplish. The ancient art interpretations are more interpretive than evidential. The objects that are read as spacecraft or spacesuits are typically objects from visual traditions that have no other examples, whose interpretation is contested among specialists, and whose resemblance to technological devices is in the eye of the interpreter rather than in any objective feature of the object. The figures that look like astronauts to some viewers look like depictions of local gods or ceremonial figures to specialists in the relevant cultural traditions. The resemblance is real, but the resemblance is between the object and a category that the interpreter brings to the object, and the category is not the only possible one. The mythological parallels are real in the sense that multiple ancient cultures do have myths involving powerful beings from the sky who interact with humans and confer gifts of knowledge or civilization. The hypothesis that explains these parallels as memories of actual extraterrestrial contact is one possible explanation. The anthropological and psychological explanations are others. Myths about sky gods arise independently in many cultures because the sky is genuinely awe-inspiring, because weather and celestial phenomena have dramatic effects on agricultural and hunter-gatherer societies, and because the human mind's tendency to attribute agency to natural phenomena produces gods wherever powerful phenomena exist. The parallel development of sky god myths across cultures is expected on these grounds, without requiring a common source and actual contact. But the mainstream dismissal of ancient astronaut claims sometimes goes too quickly past the genuine puzzles in the archaeological record. There are specific sites and specific objects whose anomalous properties have not been fully explained by mainstream scholarship. The Baghdad Battery, a set of clay jars with copper cylinders and iron rods that some researchers believe functioned as electrochemical cells, is either a remarkable anticipation of modern technology or an artifact whose function is genuinely unclear. The Antikythera mechanism, a bronze device recovered from a shipwreck and dated to approximately 100 BCE, is a mechanical computer of extraordinary sophistication that calculates astronomical positions and eclipse cycles with a complexity that was not thought to be within the technological capability of the period. It is not explained by extraterrestrial contact, because it is clearly within the tradition of Greek mechanical engineering, but it demonstrates that ancient capabilities are consistently underestimated. The genuine anomalies in the archaeological record are anomalies because ancient human capability is incompletely understood, not because extraterrestrial contact is the required explanation. The history of archaeology has been a steady expansion of understanding of what ancient civilizations could accomplish, and each expansion has reduced the category of things that required unusual explanations. The things that remain unexplained are fewer and smaller than they were a century ago, and the trend is toward reduction rather than expansion. The connection to the Fermi paradox is specific. If extraterrestrial contact did occur in the ancient past, the Fermi paradox is partly solved. We would not be in a universe that is silent at the scale of electromagnetic communication without any contact ever having occurred. We would be in a universe in which contact occurred, but was so long ago that its traces are ambiguous. The silence of the radio sky would still require explanation, but the more fundamental question of whether we are alone would have a different answer. The evidence for ancient contact is not sufficient to conclude that it occurred. The evidence is consistent with ancient contact, but is also consistent with, and in most cases better explained by, the ordinary operation of ancient human civilizations, with capabilities that are regularly underestimated. The hypothesis requires positing entities whose existence we have no direct evidence for, which is not ruled out, but is also not supported. The pyramids stand. They were built by people who are more capable than we usually credit. And the question of who taught them has the same answer. It has always had, which is that they taught themselves, over a very long time, in ways we're still working to understand. Chapter 22. The Fear of the Answer. There is a thought experiment that Stephen Webb poses in his book on the Fermi paradox, a thought experiment that inverts the usual emotional valence of the search. Most discussions of the search for extraterrestrial life are framed around the excitement of a positive discovery. The confirmation of life elsewhere would be among the greatest scientific discoveries in history. It would expand the scope of biology from a single example to a pattern. It would tell us something fundamental about whether life is a common or a rare phenomenon in the universe. It would answer one of the most ancient questions that the human mind has entertained. The search is motivated by the desire to find, and the discovery is framed as unambiguously welcome. Webb's inversion is this: when the news of the discovery arrives, before the celebration begins, take a moment to ask what the discovery implies. Not what it implies about life in the universe in general, but what it implies specifically about us and about what lies ahead of us. Because the answer to that question depends entirely on where the life was found and what kind of life it is, and the specific implications of different discoveries are very different from each other, and some of them are not welcome at all. Begin with the best case for the conventional framing. We find evidence of ancient microbial life on Mars, now extinct, in samples returned by a Mars mission. Life arose on Mars, developed for some period, and then died out as Mars lost its atmosphere and its liquid water. The discovery confirms that life arose in 2 places in the solar system, which dramatically increases the estimate of how common life is in the universe. The universe is biogenic. Life is what chemistry does when the conditions are right. The probability of life on the billions of habitable planets elsewhere in the galaxy becomes very high. The universe is full of life. This discovery is wonderful news for astrobiology. Now apply it to the great filter. Life arose on Mars. Life arose on Earth. In both cases, life arose as simple microbial life, and in the Mars case, it never progressed beyond that. The filter between the origin of life and the development of complex multicellular life is not the filter between chemistry and life. That filter, the origin of life, was not a filter at all. It happened in 2 places in the solar system alone. The filter must be elsewhere. It must be somewhere between the origin of life and here. Somewhere in the sequence of steps that Earth took, but Mars did not. Or somewhere in the sequence of steps that no other civilization in the galaxy has managed to complete. Or the filter must be ahead of us. If life is common and complex life is not significantly rarer, and if intelligence and technology are not significantly rarer, then the filter must be at a step that technological civilizations reach and fail to pass. The step that every other civilization in the galaxy has reached and failed to pass. The step that we have not yet reached but are moving toward. The discovery that life is common is, on this analysis, evidence that the great filter is ahead rather than behind. That we have not yet passed the improbable step. That the galaxy is silent not because life is rare, but because technological civilizations die at a stage of development beyond where we currently are. The philosopher Nick Bostrom has made this argument explicitly, and has concluded that the discovery of microbial life elsewhere in the universe would be, despite its scientific significance, a cause for concern rather than celebration. The more common life is, the less likely that the filter is in the past. The less likely the filter is in the past, the more likely it is ahead. The more likely it is ahead, the worse our prospects become. The best possible news for our long-term survival, given the Fermi paradox, would be the confirmation that we are completely alone, that no life has ever arisen anywhere else, that the origin of life on Earth was a singular and extraordinarily improbable event that will not be repeated, that the filter is behind us in the most extreme possible way. The discovery of a signal from an extant technological civilization would have different implications depending on what the signal reveals. A signal from a civilization that is roughly at our level of development would tell us that civilizations like us can survive long enough to make contact, which is somewhat reassuring. A signal from a civilization that is vastly more advanced would tell us that some civilizations survive and develop enormously, which is also somewhat reassuring. But any confirmed contact would require confronting the dark forest logic. The signal tells them where we are. The question of whether they intend harm cannot be answered by the signal alone. The question of whether responding to the signal is safe cannot be answered by anything we currently know about the character and intentions of other civilizations. The confirmation that we are not alone would immediately introduce the question of whether not being alone is dangerous. Some astronomers have made strong statements about the risks of deliberate transmission, arguing that sending signals into space without knowing who or what might receive them is reckless in ways that are disproportionate to the potential benefits. The astrophysicist Stephen Hawking, whose enthusiasm for space exploration was well documented, repeatedly warned against attempting to make contact with extraterrestrial civilizations on the grounds that advanced civilizations might be dangerous. His argument was that the history of contact between civilizations at different levels of development on Earth has consistently been harmful to the less developed party, and there is no obvious reason to expect the dynamics of interstellar contact to be fundamentally different. There is a specific and uncomfortable feature of the fear of the answer that is worth naming directly. The fear is rational. It is not the irrational fear of the unfamiliar or the xenophobic fear of the other. It is the fear that arises from applying the logic of the Fermi paradox carefully and following its implications where they lead. The logic says that if life is common and intelligence is common and technology is common, then the silence requires explanation. The explanations available are not all comforting. Some of them suggest that the silence is a consequence of something that happens to civilizations at our stage of development and that we have not yet encountered. The confirmation that life is common narrows the range of explanations toward the ones that are not comforting. The discovery will be celebrated. It deserves to be celebrated. And then, in the quiet after the celebration, the calculation begins, and the question it produces is the question that the discovery makes more urgent. Chapter 23. The loneliness that is also a gift. There is a version of the silence that is not a problem to be solved. Not the version that points toward a filter ahead of us. Not the version that suggests we are being watched or hidden from. Not the version that indicates we arrived too late or are looking in the wrong direction. A version that is simply what it appears to be, an empty universe. A universe that has produced stars and planets and galaxies in abundance and has produced life once, here, in this one specific configuration of chemistry and circumstance and improbable luck. And that is otherwise quiet in the way that a universe without life would be quiet. A universe in which we are, genuinely and totally alone. The emotional response to this possibility covers a wide range. The loneliness version of the reaction is the one most commonly discussed. The image of a civilization marooned on a small planet in an immense and indifferent universe, calling out into a silence that will never answer, carrying the full weight of consciousness in a cosmos that produced it once and apparently found the production unremarkable enough to attempt only once. This response is real, and the loneliness is real, and it is worth taking seriously rather than dismissing as excessive sensitivity to a philosophical possibility. But there is another response to the same possibility, one that the astronomer and writer Carl Sagan pointed toward in his own way. One that the silence makes available in a form that a noisy universe would not. If we are alone, if the emergence of life and intelligence from chemistry is the extraordinary event that the silence suggests it might be, then what exists here is not the ordinary output of a universe that regularly produces such things. It is the only place in the observable universe where matter has organized itself into a form capable of experiencing anything at all. The only place where the universe is aware of itself. The only place where the fact of existence is registered and wondered about, and felt as the extraordinary thing it is. The biologist E.O. Wilson spent his career documenting the diversity of life on Earth, the millions of species in the billions of years of evolutionary history, and the complex interdependencies that constitute the living world. Near the end of his life, He wrote with increasing urgency about the importance of preserving that diversity, not just for its practical value, but because of what it represents. If we are alone, then the living world of Earth is not a sample of what the universe produces. It is the whole of what the universe has produced in terms of biological complexity. Every species is not one of many types of organisms scattered across the galaxy. It is one of the only types of organism anywhere. Every individual organism is not one of trillions living simultaneously across thousands of inhabited worlds. It is one of the only organisms there are. This changes the moral weight of what is happening here. The extinction of a species is not the loss of one example from a universe full of examples. It is the permanent and irreversible loss of something that exists nowhere else and will not be produced again. The destruction of an ecosystem is not the damage to one of many comparable ecosystems distributed across the inhabited worlds. It is the reduction of the only biological complexity that exists in the universe that we know of. The urgency of preservation becomes different when the thing being preserved is unique, not just in the sense that no two things are identical, but in the sense that nothing remotely like it exists anywhere else in the observable universe. The same transformation applies to human experience. If we are alone, then consciousness is not a common property of matter organized in certain ways across a universe full of places where matter has been organized in those ways. It is a phenomenon that has occurred once, in a specific form, on a specific planet, in a specific galaxy, during a specific period of cosmic time. The experience of being aware, the fact that there is something it is like to be a conscious being, the astonishing and irreducible interiority of experience, is not replicated elsewhere in any form we know of. It is here, now, in the beings that have it. The ordinary moments become different when considered from this angle. Not more valuable in the sense of being rarer in a market of comparable goods. There are no comparable goods. The experience of watching light change across an afternoon, the specific quality of a conversation that goes somewhere neither participant expected, the feeling of music that finds something in the body that words cannot reach, the particular texture of grief or joy, or the complicated mixture of the two that most significant experiences produce. These are not common phenomena in a universe where common phenomena of this kind are occurring simultaneously on a million worlds. They are the only phenomena of this kind that are occurring anywhere. The cosmologist Martin Rees has described what he calls the future of humanity in the universe. The potential for life originating on Earth to eventually spread across the galaxy and beyond, to become the civilization that populates the universe with intelligence, to be the source from which all future consciousness derives. On the assumption that we are alone, this potential is not just one possible future among many. It is the only path by which the universe ever becomes more aware of itself than it currently is. The future of life in the universe depends on what happens here, on this planet, in the centuries and millennia ahead. Not because we are the most important example, because we are the only example. This is a weight as well as a gift. The loneliness of the alone universe is real, and the sense of responsibility that comes with being the only form of life that will ever, as far as we know, have the capacity to survive and spread and continue is genuinely heavy. But the gift is also real. The value of what is here, of what has happened here, of what is experienced here, is not diluted by the existence of comparable value elsewhere. If we are alone, the value is concentrated in exactly the way that scarcity concentrates value. But this is not ordinary scarcity. It is absolute uniqueness in a universe of observable size that dwarfs comprehension. The silence, if it means we are alone, is not an emptiness around us. It is the measure of how much is here, and how little, by comparison, is anywhere else. Chapter 24. The generation that might know. There is a telescope currently pointed at the sky that was not available to astronomers 10 years ago, and that has changed what is possible in ways that were anticipated in general, but that have already produced specific surprises in their details. The James Webb Space Telescope, launched in December 2021 and operational by mid-2022, observes in infrared wavelengths with a sensitivity that allows it to analyze the atmospheres of planets orbiting other stars. Not to image those planets directly, which the distances involved make impossible with any instrument currently conceivable, but to study the light of their parent stars filtered through their atmospheres as the planets pass in front of those stars, and to identify the specific chemical signatures that the filtering reveals. The telescope can detect the presence of water vapor, carbon dioxide, methane, and potentially oxygen and ozone, the molecules that on Earth are associated with biological processes in the atmospheres of planets dozens of light years away. The results so far have been preliminary and in some cases puzzling. The telescope has confirmed the presence of carbon dioxide in the atmospheres of gas giant planets, which is expected from the chemistry of such planets. The detection of potential biosignatures in the atmospheres of small rocky planets, the Earth-sized worlds and the habitable zones of their stars, is technically within the telescope's capability for the most favorable cases, but has not yet produced a confirmed detection. The habitable zone rocky planets are small, and their atmospheric signals are faint, and the number of transits required to build up a statistically significant signal is large. The telescope is doing what it was designed to do, and what it was designed to do is not sufficient on its own to confirm or rule out life on any specific world in a short time frame. But the telescope represents a qualitative change in what is possible rather than a quantitative improvement on what was possible before. For the first time in the history of astronomy, we have an instrument capable of detecting the chemical signatures of biological processes in the atmospheres of planets beyond our solar system. The detection threshold is high, and the number of suitable targets is limited by the requirement for planetary transit across the star's disk as seen from Earth, a geometric alignment that only a fraction of planets provide. But the principle has been established. The technology exists. The observations are in progress. The extremely large telescope, under construction in Chile and expected to begin operations in the late 2020s, will add another qualitative step. With a primary mirror 39 meters in diameter, it will collect more light than any previous telescope and will have the capability to directly image some nearby exoplanets, separating their light from their star's light rather than inferring their properties from the transit method. Direct imaging cannot resolve the disk of the planet at these distances, but spectroscopy of the planet's light directly, rather than filtered starlight, would allow chemical analysis with less ambiguity than the transit method provides. The LUVOIR mission, a proposed large space telescope that would be specifically designed for exoplanet atmosphere characterization, would represent another order of magnitude improvement in capability if it is built. The mission is in the concept phase and has not received funding approval, but it represents the direction of thinking in the community about what would be required to conduct a systematic survey of nearby habitable zone rocky planets for biosignatures. The timescale for such a mission, from concept to launch to meaningful results, is measured in decades rather than years. The search for radio signals continues in parallel. The Breakthrough Listen initiative, funded by the Russian entrepreneur Yuri Milner starting in 2015, is the largest and most systematic SETI effort ever conducted, using telescope time at major observatories around the world to survey 1 million nearby stars and 100 nearby galaxies for signals across a wide range of frequencies. The initiative has produced the most sensitive and most comprehensive searches of the radio sky ever conducted, and has found no confirmed extraterrestrial signal. The null result is itself informative, setting upper limits on the prevalence of certain types of transmitters in the surveyed region of space. But the absence of a detection in the Breakthrough Listen survey, while negative, is not evidence that no signal exists. The sky is very large, and the survey, however impressive, has sampled a small fraction of it. Within our own solar system, the search for life has entered a period of accelerated activity. The NASA Perseverance rover is conducting the most capable search for biosignatures in Martian rocks that has ever been attempted, and a future sample return mission will bring selected samples back to Earth for analysis. The Europa Clipper mission, launched in 2024, will conduct detailed surveys of Jupiter's moon Europa, whose subsurface ocean makes it one of the most promising candidates for extraterrestrial life in the solar system. The Dragonfly mission, planned for the 2030s, will fly a drone helicopter across the surface of Saturn's moon Titan, where lakes of liquid methane and a rich organic chemistry create conditions that might support a form of life utterly alien to anything on Earth. These missions are designed primarily to search for biosignatures, the chemical and physical evidence of biological processes, rather than for intelligence. The discovery of microbial life on Mars or in Europa's ocean would not directly address the Fermi paradox in the way that a radio signal from another star would, but it would transform the terms of the discussion. Life in two places in the solar system would establish that life is common, with the implications for the Great Filter that the previous chapter discussed.
Life on Titan would be more revolutionary still, because life in liquid methane at very low temperatures would be so different from Earth life that it would demonstrate the possibility of life based on entirely different chemistry, dramatically expanding the range of environments that could support biology, and therefore the range of places in the universe that might harbor it. The generation alive today is the first generation in human history to have the technological capability to search for extraterrestrial life in ways that have a realistic chance of success within decades. Not the first generation to ask the question, not the first generation to develop frameworks for thinking about it, the first generation to have instruments sensitive enough to detect biosignatures in exoplanet atmospheres, to directly analyze the environments of potentially habitable worlds in our own solar system, and to conduct systematic radio searches of the galaxy at sensitivity levels that would detect signals comparable to our own most powerful transmissions at distances of tens of light years. The answer may not arrive within decades. The most important searches are in their early stages, the targets are many, and the instruments are limited, and the universe is under no obligation to make the search easy. But the answer might arrive. A biosignature in an exoplanet atmosphere that cannot be explained by any known abiotic process. A signal in the radio data that has no natural explanation. A Martian rock sample that contains something that could only have been produced by life. Any of these could arrive within a single human lifetime. The generation that might know is the one reading this, and the answer, whatever it is, will not leave the world the same. Chapter 25. The silence that speaks. There is something that the silence has been doing across all 25 chapters of this conversation. Something beyond its function as the central puzzle of the Fermi paradox, beyond its role as the evidence that requires explaining, beyond its status as the fact that all the theories have been attempting to account for. The silence has been a mirror. Every proposed explanation of why the universe appears empty reflects something about the civilization doing the explaining, about the fears and the values and the self-understanding of the beings who have sat with this question and generated these answers in response to it. The great filter ahead of us reflects our awareness of our own fragility, our recognition that the capabilities we are developing may be the capabilities that end us, our collective anxiety about whether we are building something we will be able to control. The dark forest reflects our knowledge of what happens when civilizations encounter each other across asymmetries of power, the historical record of every contact between the powerful and the less powerful that we have witnessed on our own planet. The civilization turned inward reflects our growing recognition that the constructed environment has become more compelling than the natural one, our uncertainty about whether the pull of the inner world is a fulfillment or a failure. The zoo hypothesis reflects our sense of vulnerability, our awareness that we might be observed and managed by something more powerful, our complicated feelings about autonomy and protection. The silence is a Rorschach test of civilizational consciousness, and the answers it generates tell us as much about who we are as they do about why the universe is quiet. What the silence has definitively taught us, across the 7 decades since Fermi asked the question and the centuries of astronomical observation that preceded it, is the scale of our own situation. The universe is 14 billion years old. It contains 2 trillion galaxies, each containing hundreds of billions of stars, most of which have planets. The matter of the universe has had an enormous amount of time to organize itself, and it has organized itself into an extraordinary variety of structures, from quantum foam at the Planck scale to the cosmic web that spans the observable universe. In all of this, in the whole of what our instruments can reach, we have found one example of life, one example of consciousness, one example of a civilization that has looked out and wondered what else is there. This could mean we are ordinary, one of an enormous number of examples that we simply have not found yet. The silence is a measurement gap, not a fact about the universe. And the truth is a universe full of life that our instruments have not been sensitive enough to detect, and our search strategies have not been clever enough to find. This interpretation is comforting in the sense that it preserves the hope of company, the possibility that the question has an answer that is not terrifying, the chance that the silence ends. This could also mean we are extraordinary, one example in a universe that has been trying for 14 billion years and has produced only once the specific sequence of improbabilities that generates life and consciousness and the capacity to wonder about the question. The silence is a fact about the universe, not a measurement gap, and the truth is a universe in which the emergence of anything like us required conditions so specific and a history so contingent that it is effectively singular.
This interpretation is lonely in a specific and irreversible way, but it is also, if you follow it all the way to its conclusion, the interpretation that makes what exists here the most extraordinary thing in the observable universe. The question has not been answered. The silence continues. The searches continue. The theories continue to be generated and examined and found wanting, and replaced by other theories that will also eventually be found wanting. This is not a failure of the enterprise. It is the enterprise operating correctly, doing what science is supposed to do when confronted with a genuine mystery, which is to generate the best possible account consistent with the available evidence, to hold that account provisionally, and to keep looking. What requires something more than scientific methodology, something that the Fermi paradox specifically demands and that not all questions demand, is the courage to sit with the question without demanding that it resolve in a direction that is comfortable. The question of whether we are alone is not like most scientific questions, because it does not only have scientific implications, it has implications for every framework by which human beings have understood their place in the universe. For religious frameworks that locate human significance in a relationship with a divine creator. For secular frameworks that locate human significance in the rational capacity of consciousness. For existentialist frameworks that locate significance in the choice to create meaning in an indifferent universe. Every framework is touched by the question, and the answer, whatever it turns out to be, will require adjustment. The particular kind of courage the question demands is the courage to find what is there rather than what we want to find. The history of science is full of cases where the answer was not what the searchers were hoping for, where the universe turned out to be organized in a way that challenged rather than confirmed the prior picture. The Earth was not the center of the solar system. The solar system was not the center of the galaxy. The galaxy was not the center of the universe. The universe was not static. The universe began. At each step, the picture changed, and the changing was disorienting, and the disorienting eventually became enlarging, because the actual universe turned out to be larger and stranger, and more interesting than the picture it replaced. The answer to the Fermi paradox will do this again. Whether the answer is that we are alone, which would transform the moral significance of everything here, or that we are not alone, which would transform the scientific and philosophical picture of what the universe is, or something stranger than either of these, which is entirely possible in a universe that has repeatedly revealed itself to be stranger than anticipated, the picture will change. The change will be disorienting and then enlarging, because the actual universe is larger and stranger and more interesting than any picture we have so far managed to make of it. The silence has been speaking for as long as there have been beings capable of listening to it. What it has been saying is not yet clear, but the saying is real, and the listening continues, and the generation alive now is the first generation with instruments sensitive enough to begin to hear. Whether the silence says we are alone, or says something else entirely, or says something for which we do not yet have the language, the answer is out there, in the quiet, waiting, for whoever builds the ear that can finally receive it.